Test, test, test. Perfetto. Morning.
Più o meno quando ci dai come via e io ti vedo per questa quando c'è dato. E lo scrivo dammelo in chat allora, cioè faccio tutto in chat così ti chiudo io. Qualcuno volontario vuole spostarsi davanti? Any volunteers to be in the first row?
Go ahead.
Yeah, go ahead. Come on, come on. I will not... non interrogo.
Ma oggi andava avanti col programma. Domanda, settimana prossima anche dal vivo?
Sì,
Che non posso venire, proprio.
Okay, you get me. Welcome back to the Plan B program. You know the drill at this point. This is the foundations part, and we are getting to the fourth lecture, if you include the presentation introduction one, or the third, if you go with the notation of the zero as the first, like in computer science. You know the drill already. So we started with why Bitcoin. We arrived from collectibles to fiat money, digital fiat credit. We argued that was bad for privacy, so we moved to eCash. We argued that was bad for censorship, basically, and we moved to reusable proof of work. We argued that was bad for lack of fair, trustable chronology, and we moved to a blockchain. Now, before we go over, I will review a little bit with you the concept of blockchain. I did it 2 days ago in a very, very fast way. It was pretty late. It was after 3 hours of content. So now we will go through that again more systematically. And then we move over to the Lightning Network, to the issuance of assets on top of Bitcoin, whatever that means. And then at the end, to a little bit of expansion over protocols about identity, reputation, communication more in general, that may be Bitcoin contiguous or Bitcoin inspired. And that's the lecture for today. So we start again from the chapter Chain of Time. Actually, funny thing is that we all say blockchain all together, but blockchain is not really a term that Satoshi Nakamoto ever used, ever. In the white paper, he's talking about chain of blocks. In some blog post, he will name chains, a chain of proofs of work. And then in the code of Bitcoin, the first Bitcoin client release, he will name it time chain, the chain of time, because the idea is that this chain is a chronology chain, is the chain of time. Then people started to say chain of blocks, chain of blocks. Then somebody started to say blockchain, separate words, around 2012, I would say 2011, 2012. And then around 2013, it arrived on news, mainstream news, as a single name, sometimes capitalized with the capital B, and it became a buzzword to indicate whatever. Like, yeah, we do a blockchain, and it's from 2015. I would go into this a little bit more, but even Disney created their own blockchain, the Disney Corporation. It was called Dragon Chain, and even an iced tea company created a blockchain. So, and they also put the name blockchain in the name of the company, iced tea blockchain, and the stock of the company skyrocketed in the same day. So it was a huge hype. Now finally it's almost dead, but we are going back to the original definition of Satoshi, which is chain of time, time chain. Now, one of your possible teachers next month, which is Peter Todd, which is the guy that we mentioned in the last lecture, is against this definition, but he's wrong, and I'm right. So chain of time. Let's go through that again. The first things to remember is timestamps. I already went through this very, very quickly on the whiteboard 2 days ago, but let's do it again a little bit more systematically. So we start from classified ads. Classified ads are those pages in newspaper where you can just, readers can just pay to publish something. And there is a scarce space, of course, and people will pay to publish. And you can publish your documents. If you publish your document, you give a proof of the time of your document, as we said, because it would be very expensive for whoever wants to change history to go to Retire for Commerce all the old copies of the newspaper and to convince the newspaper editor to print a new fake one. So it's pretty good as a timestamping, but it's bad because there's no privacy. You have to share your documents. Also, your document may be big. So we discussed hashes. So instead of publishing on the classified page, on the advertising, instead of publishing the document, you publish the hash. But that's also not very scalable because if you have 1 million people that want to do that, or even just 1,000 people, you need a very, very big advertising page. And that's very expensive. And also it's a waste of space because you just get this page full of random numbers, which are the hashes. So you can do what you can see in the image, which is a Merkle tree. A Merkle tree, as we said 2 days ago, is a hash construction in which you hash something and you hash something else. Then you put the two hashes together. This is a message. And then you hash this. And then you hash something else. And then you take the two hashes together and you hash this. And now if you want to, in a simple hash, if you have the hash and you want to prove that you added the document before, since the hash is pre-image resistant, you just show the document. Everybody can check that the hash is correct, but nobody could basically create a document, forge a document to satisfy that hash. So you know that it's safe. It's a proof of existence. Now, if you have a Merkle tree, instead of just the document and the hash of the Merkle root, the one yellow on top, you have to show the document. And for example, if you want to prove age A, to prove the document A, you have to show the root, which is age A, B, C, D, E, F, G, age, which is on the newspaper classified ads page. Then you also have to show age B, the hash of documents B, and also age CD, the hash of the hashes of age of C and D, and then also age E, F, G, age. So basically, you show there is a newspaper with one hash, the root. Then you have to show other three hashes, HB, HCD, HEFGH, like the diagonal, like this. Of course, in these documents, seems like it's not a great saving of space, but it is, because if you expand this tree, you can go to millions of documents with a very, very low number of proofs. Also remember, it's not all these proofs that have to go on the newspaper. In order to prove your timing on the newspaper, you just need the root. That's the only thing you have to publish. Everything else, you have to keep it for yourself. You just have to back it up and not to lose it. And then you can always prove timing. So this was a thing that was existing already. There was another thing missing, which is, as I said already, what if they want to change a single document proof and they invest a lot of money to compromise the newspaper editor to print a fake version of a newspaper of 2 years ago, and then they go around in the libraries, public libraries, to destroy all the copies in the hemerotext. What if they do that? Well, in every single maker root, you also add another thing, an hash chain. You add the hash of the day before. So that changes the hash of today. That means that if you go to a newspaper 2 years ago, you change it. Now you have to change also every newspaper from that day on, which becomes enormously expensive. Of course, this gives you a gradual proof of time. The newspaper of yesterday maybe can be changed, but it's tricky because it was yesterday. Everybody will realize it. The newspaper of 1 year ago, now you have to change 365 newspapers. That's pretty expensive. The newspaper from 10 years ago, it's even more expensive. It's a linear growth, of course, but it's significant. So, okay, you have the ads, you have the Merkle tree, and you have the hash chain of the Merkle roots. Is that clear? The company that you can see there, Guard Time, was doing this already since the early 2000s. So this is not something that came after. It's funny because a few companies were doing this. One of these companies, KSI, they basically now, if you go on their website, I did have the screenshot, but I will show you later. Now they tell you, we are doing blockchain since 2001, which is, I mean, in this sense, it's true. They were putting hashes on newspapers in 2001 already. The concept of blockchain was, of course, never existing, but in a sense, they were doing that with newspaper. Now, we want to fix reusable proof of work of Alfini to get rid of the mint, the trusted mint, which is using trusted hardware, and we want to replace that chronology mechanism with something like this. Can we trust newspapers? In general, no. For time stamping, maybe, but it's not a very long term. It's a very, I mean, which country are you in? What is the newspaper fails, goes bankrupt? It's not a very robust mechanism. So let's use something which is not newspapers. Can we do that? Well, there is this idea that we announced yesterday, but now we go a little bit more into that, to reuse proof of work. We are already using proof of work for scarcity of the asset. We already say that if we let anybody inside the eCash to issue their own banknotes, everybody will issue billions to himself. So everybody will be billionaire and the money will be worth nothing, infinite inflation. So proof of work puts a limit on that, because when Alice wants to issue to herself something, she needs to actually make a proof of work. And we say the proof of work is always linear. If you want to make 2, that costs 2. If you want to make 2 millions, that costs 2 million. There are no economies of scale. Now, you will see a little bit that's not entirely true, because, of course, if you have a big farm, you can make economies of scale in buying the machines or in refrigerating. So there are economies of scale. But at least you know that the amount of machine time scales linearly with the activity. So that's not bad. So if we use already proof of work to create scarcity in the asset, can we use proof of work to create scarcity in time, in chronology, in the definition of time? So can we use proof of work to replace the newspaper? Why? So let's go back to this. Why is this safe? Because of cost. In order to change the past and to fake a time relationship, in this kind of example, the attacker will have to pay the newspaper company to make a fake copy, and they will have to pay everybody with a real copy to destroy it or to retire it, at least from trusted sources like public libraries. That's a cost. If you do hash chain, so if you do that in every Merkle root, you put together the Merkle root of the day before, and then you take the hash of both Merkle roots. If you do that, in order to change a copy, you have to change the copy and every copy after that. That increases the cost. So proof of work is, and we already defined that, is a cost function, is something that creates a cost for somebody. So the intuition was, what if we reuse proof of work, not only for creating scarcity in the issuance of the asset, but also to create scarcity in the, let's say, in the definition of the chronology of asset transfers. So we can remove the central mint of reusable proof of work, the central computer, the server of Alfini. Can we do that? Well, it turns out we can. How do we do it? Actually, Nick Szabo, that I already mentioned before, who just recently blocked me on Twitter, I don't know why, and he basically had this idea already in around 1999, but he started to publish the idea around 2004, and then there was a, well, it's pretty chaotic, but the last blog post about that was in 2006, and he created this idea called bit gold, and the idea of bit gold was, okay, we need to get rid of the mint. We have proof of work. Maybe we can do a network of computers that are voting on the history, and they use proof of work as the voting coefficient. Because if you don't have a coefficient, if you have an open system where everybody can participate, and you just vote on the history, then it turns out that everybody can create 1,000 fake nodes just to vote on their own chronology. So Alice can send you the proof of work, and you will give then Alice will vote with everybody else. They will vote on this chronology. Then Alice will create another copy of the transaction, which is giving back the money to herself, and she will spin up 1,000 new fake notes that are all controlled by her. Then she votes again, and then you have a new majority voting for another chronology, of course. And if anybody was outside of the system, they cannot trust one or the other chronology. Even if you were live during the system, you were seeing that. So you will see one chronology, and then suddenly you see the majority change. You see that, but you cannot prove that to anybody connecting now. So either all the participants are always monitoring the network, which means that nobody can enter this new network. It can only work for the original group of people starting, and everybody else must join later and must trust everybody, or you need something better. So the full history here is that another cypherpunk named Wei Dai, he actually created an idea to try to compensate for this. The idea was what today is called proof of stake. So the idea was that instead of making everybody vote, you select a small group of participants that can vote, and they have to put some proof of work in a locked address, and they vote proportionally to the amount in the address. That's called proof of stake now. The problem is that this is broken, because how do you know that you locked the money in the address? Well, you need a chronology where you transfer the money to the address. But what is proving the chronology? Well, it's the voting on the chronology. So it costs you nothing to vote in different chronology, because in one of them, you have the money on the chronology. On the other, you have the money on the other chronology. So you need something like slashing, which is now called slashing, which is basically a social mechanism and not a technical mechanism. And then you go back to what today shitcoiners, that's the technical terms, call weak subjectivity. So it's a mess, basically. It doesn't work. If you are interested in that, there is a 2015 paper by Andrew Polstra, which mathematically proves that this cannot work in a decentralized fashion. Of course, it can work in a centralized fashion. So if you have a central authority, it does work great, because you don't need it. The paper is called On Stake and Consensus, Andrew Polstra, and you can just find it pretty easily on the web. Now, so instead of newspaper, we use the proofs of work. So you issue the proof of work to generate the asset, and in every proof of work, you also include the Merkle root of all the other transactions that you're seeing, plus the Merkle root of the day before. So you're basically replacing everything. And of course, now the question is, why should you do that? Newspaper were doing that because you were paying them. You pay newspaper with fiat, and they will publish your advertising. If you make it free, it will become super crowded, and there will not be space for anybody anymore. So you have to pay them, basically. This is the same. So the idea is that you create the concept of fees. So if you go, I had this mempool.space. Oops. I had this here, and here, let's take a block. Or actually, I have it right before. This is the right way, not the Japanese way. And you enter here, you take a transaction. You see there are many, many inputs. This is a very good transaction. Many, many, many inputs, a big output, smaller output, smaller output. This is not really an output because this is going to a new public key. This is going to a new public key. This is going to a new public key. But this is output number 0. This is number 1. This is number 2. This is not an output. This is this tiny thing here. This is the fee. The fee of the transaction doesn't go anywhere in terms of public key, but it's the right of everybody creating a new proof of work that will incorporate this transaction inside the Merkle root. So if you put the Merkle root, so instead of A, B, C, D, E, F, G, you have transactions of reusable proof of work. If you include this transaction and the Merkle tree inside your proof of work, you will collect all the fees of the transaction. What are the fees? Well, you do all the inputs minus all the outputs and just check the difference. So if in a transaction you have 3 units of proof of work coming in and 2 units of proof of work coming out, there is 1 unit of proof of work which is left for somebody to collect. That somebody is the worker that will create the proof of work. And this process is called mining. Now, it's interesting because proof of work in itself seems like a little bit mining in a mine because you have to do work to extract gold. Satoshi Nakamoto used the term mining to indicate this process because it was actually a little bit similar, analog to the idea of mining gold. And then, as I will explain now, the figure of speech of mining also has to do with halving because eventually the gold mine will deplete and will be less rich of gold, which makes sense. But now the concept of fees is very important to mining, but is not very fit in the analogy. We have to imagine a special kind of gold in which every time people pass gold from one end to the other, the gold basically leaves out a little bit of gold powder. This gold powder basically go back down to the ground, and any miner that will basically work on that square meter of ground will extract not only the new nuggets, the new ores from the ground, they will also collect all the powders of all the people that exchanges money. Wow, this is a weird metaphor, but it's the way Bitcoin works. So not only you're extracting scarce material from the ground, which is the proof of work, the proof that you spent energy, but you're also extracting from the ground all the fragments of the transactions of the other people that transacted above the ground. So you just have to update your gold metaphor to these weird things. Not only this is important, but this is so important that in the white paper, so we will check the white paper of Bitcoin, which Satoshi presented, published in the cryptography mailing list, which is a mailing list which is basically the derivative of the original cypherpunk mailing list in Halloween 2000, during Halloween 2008. Not only in the white paper, there is a lot of stuff missing. The white paper doesn't describe the 21 million cap. It doesn't describe smart contracts at all. There are also a few mistakes that we can examine a little bit. I gave a lecture about all the things wrong in the white paper. There are many, but many things are also missing. But one thing is not missing. One thing which is very clear, even if it's not very well defined in the white paper, is that eventually the fee mechanism can replace the discovery of new proof of work entirely. So the idea is that you're going to phase. So initially, people will use proof of work to issue proof of work to themselves. Like Alice creates the proof of work, she proves to the world that she sacrificed some scarce resource, and she issues that to herself. That's fine. And then people will assign to themselves not only the proof of work, the sacrifice they have done, but also the fragments of reusable proof of work transfer that they have witnessed for chronology confirmation. And then eventually you phase out the new proof of work and you just rely entirely on these fees. So it's like the mine, the mine gets depleted. So you keep mining gold, mining gold, mining gold. New gold in the earth crust disappears, and whatever remains are the gold powder that keeps going back to the ground when people transact. So again, update your mental image of gold is not seems more like water. Like you keep this kind of cycle where people extract gold, they transact gold, but gold gets a little bit leaves a little bit of dust that goes down and recreates mining. So Satoshi decides a very interesting mechanism. Oh, well, by the way, down to the left, you have the idea of following the heaviest Poe chain. In the white paper of Satoshi, the concept is the longest chain. I'm saying the heaviest chain, but I will explain it a bit why. But the point is that you follow the chain with more proof of work on top of it, and then you can never be wrong. You see that the greenish square is the first proof of work. Then there is a proof of work which includes the hash of the previous proof of work. It's the hash chain. And then there are two proof of works that include it. One is yellow because it's real, it's legit, it follows the rules, but it has not been followed by the majority of the proof of work. The blue one has been followed by the majority. So the blocks are called orphaned because well, actually one is called stale, the other is called orphan. And the blue chain is the only one. The chain is not a graph. Remember that it's not a tree. A tree, like a Merkle tree, can branch. A graph can branch like transaction graph in eCash. It can branch and merge. The chain cannot branch, cannot merge. Well, can branch temporarily, but then you just kill the smaller branch and you stay on the larger branch. So this is a proof of work chain. This is what replaces newspaper in proving time. Now you don't need newspaper anymore, finally. The only utility was basically time stamping, and now it's gone. Now you have this, and then you have this equation. This equation is the mathematical equation for what Satoshi replaced, what Satoshi decided to set as the monetary policy, let's say, of Bitcoin, or even better, as the gold mining policy of this particular kind of digital gold. So even if you are not versed into mathematics, let's just at least understand these symbols, because this is a very nice, this makes for a very nice tattoo. So at least if you learn any mathematics at all, this is a very good example. So this symbol here is a sigma, which is the Greek letter for S, sound, sigma, which people uses for sum. It just means some stuff. So just it's for computer scientists out there, this is like a loop in which you sum. Like in C, it would be basically plus equal. You sum to itself. It's a loop where you keep summing. So it's saying take the letter I. This is not an imaginary number. This is not the square of -1. It's just a random index. I. Do you have the remote? Let's see. Okay. You take a variable, random variable I. You set it to 0. Now you do 210,000, which is the number of proof of works that you want to use as a period, and for each one of these period, these epochs, you multiply 210,000 for 5 billions, so 5 times 10 to the 9, or 50 times 10 to the 8. This is a multiplication. Disaster is just multiplication. This is scientific notation. 10 to the 8 means tens multiplied by himself 8 times. So basically, this is 100 millions, right? So 50 times 100 millions, which is just 5 billions, which is easier. So you have 5 billion units of proof of work for the first 210,000 proof of works. So this equation is saying the first 200,000 proofs of work that people will create, they count as 5 billion units each. Then you sum these, sum. But then you stop, because then every time you finish this sum, you move to the next phase of the cycle, and I is, so at the very first time, I is 0. So what is 2 to the 0? Is 1. So this is just 210,000 times 5 billions of units. Then I becomes 1. So now you do 5 billions half, cut in half, divided by 2, which is 2.5 billions. So the first 210,000 the first 210,000 proofs of work, they get 5 billion units of proof of work each. The second batch of 210,000 proofs of work, they get 2.5 billions of units each. So basically, the proof of work is the same from a mathematical point of view. It's just proof of work. But you are cutting in half the conventional value of this proof of work. This is interesting because this, and then you go on, of course, you go on. You don't have to do 32 here. This is a trick, but actually this is redundant, because these weird squares here indicates that you approximate for the, you basically take the ground, the integer, the highest integer which approximate this value from below, which means that when you go to 1/2 of unit, you stop, because you can just have 5 billion units, 2.5 billion units, and then 1.25 billion units. Then you go, then you get to 8 units, 4 units, 2 units, 1 units, and then stop, because these squares will just tell you, well, now stop. So here, instead of 32, you can just put infinite, and you can keep summing, but 0, 0, 0, 0, because you're approximated. And 32 is just to tell you, you can negotiate with your tattoo person if you want to put infinite there or 32, but the 32 is a good reminder that after 32 times, this will just remain 0, 0, 0, 0. So there is a minimum precision on this proof of work the definition. Now, today, we call these units set, like Satoshi. We call it 1 Satoshi, 2 Satoshis, and we abbreviate that as set. And people will fight a lot about how to say in plural. Do we say 200 sets or 200 set? And what is the symbol? There is just this weird symbol that looks like a kebab. Then there is another symbol that looks like the symbol of the SS in Germany. Many symbols that people like or don't like for different reasons. And people say, no, set is ugly. Let's just call them Bitcoins instead of set. Well, I think it's a stupid idea, but some people agree, including Jack Dorsey. So maybe we'll catch on. I hope not. Some other people say, well, the 100 million is not a very nice division. So let's say that we, instead of considering sets conventionally, let's just consider hundreds of sets, and we call them bits. I think this is even worse, because bits in mathematics and in computer science are something else. But anyway, there is a lot of confusion. Bitcoiners like to fight over stupid things. But one thing is important here, which is this denominator. So Satoshi started with this equation, and then after a while, it comes out that the initial market value of sets was very, 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 very small. Very, very, very small, which means that people were sending each other 10 billion sets or 100 billion sets or 2 trillion sets. That was very annoying. Like, I'm sending you 3 trillion sets with all the zeros. So Satoshi says, okay, let's just say that the conventional unit of one coin, I will call one coin just a group of 100 millions of fundamental units. So the fundamental unit, the Satoshi, is a real unit in the protocol. It's indivisible. It stops the halving process forever. So it's a real quantity. It's like an atom of gold. The coin or the Bitcoin, which is 100 million units, is a conventional unit. You can show that in a wallet, but it's like, say, 1 gram of gold. Sure, you can measure gold in grams or in kilos or in tons or in pound or in like in barrels or whatever you want in theory, even in liters if you melt it. So gold is just a conventional unit, but 1 atom of gold is not a conventional unit. You cannot have half an atom of gold. Atom of gold, 2 atoms of gold, you cannot have half. That's the Satoshi, the fundamental unit. Now this is if you just don't do this is how many Satoshis are issued in this system. These are how many Bitcoins, which is a conventional unit. It's a very confusing unit because initially Satoshi was calling coin what we now call UTXO. He was calling it coin because it's just the last basically it's like in every transaction the inputs are coins that they're going to basically coin that you're going to put into the oven to get them melted down, and then the new coins are forged, they are minted, they are created out of the outputs. So that's a coin. But he was also calling coins what we now call set, and he was also calling coin what we now call Bitcoin, and he was also calling Bitcoin what we now call the Bitcoin protocol. So we started to say, yeah, Bitcoin with the capital B is the protocol. Bitcoin with a small b is the unit of 100 millions of sets. As you can see, this is still very confusing. This will get better in time because people will eventually learn something, but now it's still messy and terminology is not super clear. So now we tend not to use the word coin very much anymore. We call the leaf of the graph of transaction, we call it UTXO, which is very ugly. Maybe coin was better. And we still use coin a little bit when we say coin join, coin selection, coin swap. That's the meaning of coin. The UTXO, the leaf of the transaction graph. Then we can, the idea basically of Jack Dorsey and John Carvalho of calling this stuff, this unit a Bitcoin, maybe we could call it a coin. It also makes sense. And then the conventional units, yeah, we call it let's say the unit. So I would say that we now say UTXO for the first meaning, set for the second meaning, and BTC for the third meaning, which is the conventional ticker on exchanges. 1 BTC is basically that. This is the equation. Now, there are 2 interesting things here. The first very interesting thing is that you can see here in the graph, the red one is the inflation rate. Actually, the inflation rates is already going down. You see, is already curving down because every time you add, even if there was no halving, the inflation rate eventually will go down because at the beginning you have 5 billion units. Then you have 5 billion units over 0 is infinite inflation rate. But then when you have 5 billion units, you add another 5 billion units, and that's a 100% inflation rate. Then you have 10 billion units, you add 5, that's only a 50% inflation rate. So inflation rate, even if you keep it constant, is already going down. So if Bitcoin did have a fixed amount of units without the halving, inflation will still go down in theory. But there is a problem. It will go down, but it will never stop. And if people, you have the Peter Todd problem. If everybody wants to get some Bitcoins, they will mine a lot. And so we will keep mining, even if you need a lot of time to go in that direction, you still need a lot. So if this line, the red line that is started to curve, didn't get this discontinuity, it will trend to 0, but never will reach 0, and you will still have inflation basically forever. And this seems like a good thing, but considering that the amount of time is not fixed yet, it is fixed in Bitcoin, but I didn't introduce that trick yet. It will basically go to infinite supply. And infinite supply in an undefined time frame can mean infinite inflation, as long as people will keep doing more proof of work with better machines and we keep doing more. So you have the problem that Peter Todd basically mentioned in the email, infinite inflation. So you have this inflation going down, then it hits the discontinuity, which is the end of the cycle of 210,000 proofs of work, and then it gets cut in half. And so you can see that the line is going this way, and then is going smoother, because now you have a lower inflation, and then down and down. At the end, after, so here you can say 5 billion, 2.5 billion, 1.25 billion, 0.625 billion, 0.3125 billion, 0.15625 billion, 0. And so on and so on, until you get to 8 sets, 4 sets, 2 sets, 1 set, and now it's 0. The interesting thing about this equation is that in mathematics we say it's converging. So the final amount of sets is not infinite, it's finite. It's basically 2.1 quadrillions units, or it's 21 millions of conventional units of 100 millions each. So having these finite amounts, it means that inflation eventually goes to 0. Now, this alone, it's important to people think that what I will introduce in the next slide, which is the difficulty adjustment. The difficulty adjustment will somehow fix the problem of inflation. That's true, but also not true, because this halving alone will fix the problem of inflation eventually. People will race to do more and more proof of work. You will have a lot of inflation until you hit the end of this amount, 2.1 quadrillion, that's over. There is no more inflation. Now, stock to flow scarcity is infinitely up, because the new flow is 0. Now, this is the first interesting thing. This equation is introducing absolute scarcity in the proof of work. So proof of work itself is not scarce, but halving proof of work is scarce. It arrives to a point and then you cannot produce anymore. This is a conventional scarcity, of course. Proof of work can be produced forever, but we decide conventionally in the system to consider the proof of work less and less important. Every 210,000 proofs of work, we consider it less important until we consider it not important. It's still important for the double spending prevention, for the time stamping, but we don't count it anymore as a new issuance. Basically, we only assign them the fees. This is also very important for censorship resistance. So what happens if we say that a powerful entity could just go to the newspaper and could just buy the newspaper off to change the past? It would be very expensive, but they can do it. And Bitcoin is facing a very powerful enemy, potentially, the central bank and the fiat system entirely. So what happens if somebody will pay the new miners, the people creating proofs of work, to stop including transaction? Then nobody will have a double spending protection anymore. So that's very bad. We cannot transact anymore because we don't have a mint. We don't have a protection from double spending. So the idea is that if you have fees, eventually every creator of proofs of work, every miner that refuses transaction, they will not get fees. Now, at the beginning of the issuance, they don't care because they still get the new proof of work. So even if they don't, so at the beginning of the cycle of halving, even if you ignore the transactions and you don't want to confirm other people's transaction, you still get the reward, which is your subsidy, basically, your inflation subsidy. But at the end of the cycle, either you include the other people's transactions, or if you don't, you put all your work into the machine, you spend time and energy for nothing. So at the end of the cycle, your only reward is if you include other people's transaction in your proof of work. At the beginning, that's not so. This is so we can discuss a lot about, there are a few posts by Satoshi Nakamoto. Why did you set up this mechanism? Well, I said, I don't know, it was simple enough. Why every 210,000 blocks? Well, I will explain it a little bit later, but it's a conventional number for now. Where is the 21 million coming from? Well, it's coming from this. It's coming from this, of course, right? Why you divide in half and not by 3? Yes, that's conventional. It's just simple. Why do we have a bottom where you cannot divide anymore? Well, because infinite divisibility is possible in computer science, but it's pretty complex. You have basically to create the type of a number that can be divided infinitely. Is in computer science is pretty annoying to build. You basically have to create a fraction type, which is annoying. So the idea, and even the fraction type, the denominator will have an overflow eventually. So it's not really infinitely divisible. So it's just simple, right? The consequence is the 21 million meme, or to be more accurate, the 2.1 quadrillion fundamental units. And this is basically the result. So we said, now, instead of being, so proof of work can be inflated infinitely. And if it's too valuable, people will race to inflate it very soon. And you will have a very high inflation rate. Even if it goes down, it can go down it can go down, but it can still be very high because more people will join. But the halved proof of work is infinitely scarce. You get to a point in which you cannot have it anymore. Mindful that this creates some kind of arbitrarity, because in a way you could say, well, in a reusable proof of work by Alfini, you were just counting work. If you put the work and you spend the energy, you will have the money. Here, the idea is that, no, if you put the work and you don't include any transaction, you get the money first, but then you don't get anything anymore. At the end of the cycle, if you put the work and you put the transactions, now you get the money by getting the fees from the other transaction. That's a change. But to some degree, this seems like something a little bit less elegant. But you also have to imagine that even just to measure the proof of work itself was already an arbitrary decision. In Alfini's proof of work, if you did, instead of doing work with SHA-256, you did work with another hash function, that the system will not consider it. So already, by choosing the hash function, you are introducing some level of arbitrarity. So this is the Bitcoin could have, some people say Bitcoin was not created, it was discovered as a concept of infinite scarcity, of absolute scarcity, digital scarcity, without the central party. True, but some parts of Bitcoin are arbitrary. A different civilization could come up with a Bitcoin, which is the same, but instead of being based on SHA-256, is based on another completely different hash function, because that's to some level is arbitrary. And another civilization could have a completely different number here, or could have an halving that goes down more, or instead of 5, there could be a 7. So there are a lot of arbitrary choice that Satoshi did. Now that he did them, the point is that this is a network effect. It's like there are many ways to invent the game of chess, or checker, or backgammon. Once you do, it sticks for millenniums, and you can reinvent chess, but good luck, because there is a very strong network effect on chess. It's an open protocol that everybody is using from since the backgammon even more. You cannot reinvent. Yeah, you can, but that was already ingrained into humanity from millenniums, for millenniums. So millennia. So it's hard to change it. So this is basically Bitcoin. So now you know what is the heaviest proof of work chain, which is the one with more cumulative proof of work, and you follow that, just like you follow a newspaper here. Now, there is a problem, though. The problem is that, let's go back here. In a newspaper, you just want, so with guard time, what you want to do is proof of existence, or timestamp. You just want to show that the document existed. But with Bitcoin, showing you that one transaction existed inside the proof of work chain is not enough. I have to show you that the proof of work chain contains the transaction, sure, but I also have to show to you that no contradictory transaction, which is spending the same amount, is included. So I don't have to show you a proof of inclusion. In order for you to really trust me, I have to show you a proof of exclusion. You follow me? You understand? So Alice is sending proof of work to well, at this point, we can just say it. Alice is sending satoshis, to Bob. Now, Alice doesn't have to show Bob that he did sign the transaction and the transaction was included in the chain. Alice also has to show to Bob that no other transaction spending the same coins, the same UTXOs, was created and signed. How do you do that? Unfortunately, to do that, Bob, but also Charles and also Daryl and everybody else in the loop, in the system, they not only they have to store the Merkle proofs, so the Merkle root and their own proofs. They have to store every transaction. Now, mind it, not every hash of a transaction, every transaction. Now, scalability in guard time is great because with one hash guard time, one hash per day, guard time could scale, guard time could timestamp one client, 10 clients, 100 clients, 1 million clients, 1 billion clients, 1 trillion clients. One hash, Merkle root, plus the previous day Merkle root, so the hash chain. One single advertising in the classified page. This is very scalable. What is the cost? Well, the clients, they will have to store log n, so the logarithm of the number of clients. So if you have one client, they don't have to store anything. If you have 10 clients, they have to store one proof, and then so on and so forth. With Bitcoin and Satoshis, in order to exclude the previous the fact that transaction is double spent, so guard time was not solving the double spending problem. It was just solving the certified timestamping problem, which is easier. Double spending problem means to do a proof of inclusion, which is easy with the Merkle tree, and also a proof of exclusion, which is way harder to do. To do the proof of exclusion, every participant of the system has to download and store, but now we will see the caveat there, but at least to download every single transaction ever made. That means that this system that Satoshi created in 2009 requires you to receive money today in this system to download every single transaction that has been done every single minute from 2009 until today. And in 2300, it will, in order for you to join the system trustlessly, it will require you to download every single transaction from 2009 until 2300 to that very day. Otherwise, you cannot receive trustlessly. That doesn't scale. The first problem is time, of course. So what happens if let's say that you have new proof of work coming in the system, and this new proof of work is coming on average every millisecond because there is strong competition. So new proof of work coming. Of course, this will fail because with 1 millisecond, there will not even be time for the network to agree on the last proof of work before you find a new one. And remember that this is a chain. So every proof of work must not only include the Merkle root of the transaction, it also must include the previous proof of work. So you need to agree on the previous proof of work. Otherwise, if you have a new proof of work every millisecond, these yellow branches will be very, very long, which means that there is a lot of wasted work, which means that many people will put a lot of work without any reward, which means that big miners, they can stay in business. Small miners, they go out of business because they will put a lot of work, and most of the time, the work will not be rewarded. So they will just go bankrupt. Only super big miners can survive. So having very long yellow chain is bad. It centralizes mining into few entities. So it's very, very bad. So you want to have a small yellow chain. How do you do it? You increase time between proof of work. How do you do that? Well, there is this trick, which is basically, it's called difficulty adjustment. This is very brilliant. One of the most brilliant things that Satoshi introduced. Difficulty adjustment means that you remember that hash cache had different difficulties. If you want to find a message whose hash start with 0, you just say you just do that by hand in a few seconds. If you want 2 zeros, that's exponentially harder, a little bit less than exponentially. If you want 3, 0, way more and way more. Now, the idea is that you create an algorithm in which you define that the difficulty to have a correct proof of work depends on the timing of the system. And the adjustment goes like this. If basically you take 216 2016 blocks, and if you want to remember 2016, unless something interesting happened to you during 2016, what you can do is to reverse it, and 6102 was the executive number which Roosevelt used to confiscate the gold from American people. So it's also connected to monetary history. So every 2016 proof of works, the system takes an average. The system counts the number of proof of works which are included in the blue chain. Now the system compares it with the time stamp on the first proof of work, which and the timestamp on the last. So the system says, what is the timestamp? So timestamp, literally, the every proof of work includes the time written as a Linux timestamp, a normal Unix timestamp. So that's included. So you take that, you take the last and the first, every 2016. Now you subtract, and that gives you a time. This time is usually, this time is a time. Then you compare it with the number of blocks. And the idea, you start from the number of blocks, and now you compare it with the time that passes. If this time is 2 weeks, then basically you keep the difficulty as it is. If the time is more than 2 weeks, it means that proofs of work are coming very slow. So you need to reduce the difficulty. You drop a 0. If this time is less than 2 weeks, then proofs of work are coming too fast. So you put another 0 and you increase the difficulty. And each node in the system can do this independently without any central party, and they can just reach an agreement. And that means that as an effect of this choice of 2016, basically the idea is that we have on average one proof of work every 10 minutes. If there is more than one proof of work every 10 minutes, the system will correct itself by increasing the difficulty. If there is fewer proofs of work than 10 over 10 minutes, the system will correct, reducing the difficulty. And we'll go like that. So you have more people putting work on that with better machines, difficulty goes up. You have less people, fewer people putting work, difficulty goes down. That's basically self-adjustment. That means that now we can go back to this graph, and not only we know that every 210,000 proofs of work, you have a halving. But you can say that on average, every 4 years, you get an halving. So the first halving, so you will have the system start in 2009, and then the first halving will be around 2013. The second halving will be around 2017. The other halving will be after 4 years, 4 years, 4 years. Now, a little bit less, because since the beginning of Bitcoin, the price of Bitcoin, later we will discuss the price a little bit more, the price of Bitcoin tends to go up on average. That means that the incentive to mine is going up, difficulty is following, but not following fast enough. So basically, you still have people trying to catch up with, difficulty is catching up with the price. So the halving arrives to 210,000 proofs of work require a little bit less than 4 years. Why 4 years? So now, with this adjustment, I can explain you why Satoshi selected this number. Satoshi basically selected, so you start from the difficulty adjustment to understand this number. Satoshi selected 10 minutes on average. Why? Because 10 minutes on average is how much 1 megabyte, a file of 1 megabyte will take to broadcast in a network to reach a global network of peers so 1 megabytes of file, a file of 1 megabytes, will reach every peer in a peer-to-peer network on average in 10 minutes. So he says, okay, in every 10 minutes, people will basically get the last proof of work. And now I will explain you why 1 megabyte was a good example. And then he said, when do we want the halving? Let's make it 4 years. Why? We don't know, but like leap years are every 4 years. Presidential elections in the US are every 4 years. Changes in the head of the Fed are basically every presidential election, even if not really. Like Olympics are every 4 years. So Satoshi did this in a way that Bitcoin will always have an halving the year of the presidential elections, and which will also be a leap year, and will also be the year before the Olympics. Or 2 years before. The year between the Olympics, basically. So he just selected a period that seems like very much socially ingrained into human conventions. 4 years for the halving, 2 weeks for the difficulty adjustment, 10 minutes for the separation between proof of works. So Satoshi didn't have so much. So Satoshi had a few choices. Like the first choice was how many conventional units, indivisible units, you want to put in the first proof of work. He selected 5 billions. Why? Why not? Random. Now you need a number. How do you want to reduce the proof of work? By 2, like dividing by 2, by 3, by 4, by 2. It's simple enough. That makes sense. How much time do you want between one proof of work and the other on average? I want 10 minutes. Good enough. It's the time to reach all the network. How often do you want to adjust the difficulty? 2 weeks. Okay, 2 weeks. That's what a developers will say. When is the new feature ready? In 2 weeks. So that's a very standard time. How often do you halve the supply issuance? 4 years. If you put all these choices together, you get the Satoshi equation, which is this one. Plus, how much you want to divide. So how do you want to aggregate Satoshis into one conventional units? And he selected 100 millions because the price, but that was not a natural, a conventional choice. He just checked how the people were measuring the price. We will see how that comes later. And he just said, okay, just drop a little bit of zeros because there are too many zeros here. So let's just go closer to the unit. That's just something that started from the market to a degree. Now, difficulty adjustment. The problem is that, as I said here, one Bitcoin proof of work doesn't just have to include the Merkle root and the Merkle proof. He has to include every transaction which is included. So you have to include the Merkle root and the documents themselves, the full documents. Of course, now you can already see that there is a problem of privacy, but also there's a problem of scalability. In this page of the Washington Post, this classified page can host billions of users if they want with the Merkle tree. But one proof of work of Bitcoin cannot host billions of users, because then you need billions of transactions, which must all be written in clear in the page. You need a very, very big page. So the first problem with this is that you have, of course, the first problem is timing. If you want to buy a song on a streaming service and you want to pay, in order to know that they are not being double spent, the streaming service will have to wait for mining, wait for confirmation. Ideally, even more than one, because security in this chain goes up exponentially, basically, because it goes up linearly, but then the rest of the network will compete with you in order to create the longest chain. So an attacker, to rewrite the history, the attacker let's say that the attacker wants to rewrite the history going back to the first square. What they have to do is to do all the other squares faster than all the rest of the network. There is the calculation of the probability to have an attack in the white paper. If you are versed into probability, you can check it. There is a mistake that has been corrected a few years later by a mathematician. And if you go inside the proof of work space, there is a giant mirror with all the white paper, and you can see yourself while you check the equation and you find the mistake. So still, it's exponentially hard to rewrite the past. But that's the cost of rewriting the past. That means that if Alice pays Satoshis to Bob, Bob will wait before giving the streaming service for one confirmation, maybe two, maybe 3, depending on the amounts. If it's a cheap amount, 1 confirmation is enough, because rewriting the history will cost more than the amount of money. So no attacker will spend more for the attack than what they are trying to rob. So if it's a car, maybe you want 3 confirmation. If it's a giant mansion, maybe you want 7 confirmations, depending on what it is. It's a complicated calculation, but it's possible to do it. And so now there are many, many caveats in this calculation, but at least you have the simple version. Now, streaming service, you pay, you expect to have the song immediately. Internet is fast. Instead, no, sorry. You have to wait 10 minutes. 10 minutes on average, because proof of work is a random process, you just try. You set the difficulty such that on average, that's 10 minutes. But sometimes the next proof of work will come in 20 minutes or 40 or 50 or 70, or sometimes every 1 minute, sometimes in 3 seconds. On average, it's 10 minutes. So you go there. I actually had this, like when I went to El Salvador in 2021, El Salvador was making Bitcoin legal tender, and all the main supermarket chains, super selectors, they were accepting Bitcoin on chain. So with the Satoshi system. So I went there with my grocery, I paid, let's wait for the first block. And it was 40 minutes. And Salvadorian people were very, very polite. I tried to say, let somebody else go first. No, I cannot. The system doesn't allow me. You have to go first. There was a queue of probably, I don't know, 40 people already. Yeah, exactly. Everybody was secretly hating me, but they were still smiling and being very polite. And after 40 minutes, I see on the Block Explorer, we get 1 proof of work. Finally, we have 1 confirmation. Nothing happens on the terminal. Then I tried to check the system, Chivo, and they were waiting for 2. So at this point, I took my cash dollars, I put it there, I say, that's a donation for the Chivo wallet, and I just went away. Because otherwise people were polite, but you never know. It's a very secure country, but still people can get angry for waiting for more than, 80 minutes in total in a queue. So this is very bad for scalability, very, very bad. Maybe you don't want 10 minutes. Maybe you want 1 minute. But then if you get 1 minute, the yellow branches, the orphan branches will go up. And that will make small miners go out of business. So maybe you want 1 hour. That's very good for decentralization of mining. But then you have to wait for 1 hour. So already with the difficulty adjustment, you see that we have a huge scalability problem. The more you may wait between one proof and the other, the worse the UX gets, especially for fast things. That's good. If you want a package to be basically, if you want somebody to ship you a package overseas, that's fine. Wait 1 day, whatever. But if you want digital services, which is what digital cash is especially good for, that's a disaster. So that's a problem, right? Small time means basically great UX, but centralization. Long time means terrible UX for payments, but decentralization. So we are in a conundrum. But there is another conundrum. How many transactions do you put in a market route? How many transactions can a miner include? So if there are fees, the miner will be happy to include more transactions because more money for him. So the miners will include more and more transactions. But in the Washington Post page, you have a limited number of advertising, and you cannot make the page too big. What is the limit of the page you can make in Bitcoin, basically? What is the limit of the size of the proof of work with? So you don't have to send only the proof of work. You have to send the proof of work and all the transactions that are included in the proof of work. So this thing, the package of the proof of work and all the transactions included, is called a block. Now we will see the details of the block. That's why it's a chain of blocks. And the size selected by Satoshi was 1 megabyte. Actually, it was reduced by policy, but that's a complicated thing. But let's say the consensus-wise, the rules of Bitcoin in 2009 said that late 2009, Satoshi changed the rule to limit this to 1 megabyte, basically. And why 1 megabyte? Why not? This is a presentation that was given by Tadeusz Dria, which is one of the 2 inventors of the Lightning Network, with with the other inventor Joseph Poon. Actually, they reinvented the Lightning Network that had been invented already, kind of, by Christian Decker, which is a fellow Ticino guy living here in Zurich, the year before, but it was not published because they were pending a university paper approval. So these two guys came first. Taj, that was also your teacher for the last, he may be your teacher for the summer school. We don't know. We didn't say yet. But Taj can be around. Is in the US right now, and he was working at MIT while Joseph Poon was working at Google, and they did this presentation at my second Bitcoin conference ever, which was Scaling Bitcoin in 2015 in Montreal, and they presented this bat tube, the Bitcoin failure bat tube. What they're saying is that if you make the blocks too small, so you include too few transactions, then the fees in order to be included must be very, very high because you have to compete for a very small space. So only the rich people will manage to enter in a block. And everybody else will just have to delegate like a bank. They will just have to trust the rich people to move around money for them because they cannot afford to get in a block. So sending money, if you do very, very small blocks, sending money becomes very, very expensive, and you centralize the keys. If you make the blocks very, very, very large, then sending money becomes very cheap because there is space for everybody in the block. But then blocks are very, very large, which means that to receive money, you have to be able to download every single transaction from the Genesis block on all of them, and only very, very rich people can afford to have a data center with a connection large enough to download every single transaction. So let's assume, for example, that every block is 1 terabyte. That means that you have to be able to download in every part of the world, every user must download 1 terabyte of blocks every 10 minutes. That's a lot. That's a lot already now. But consider worst case scenario, persecutions, you have to use Tor because your government doesn't allow Bitcoin. There's a war, they are cutting the cables. There's any interesting catastrophic scenario, which is where Bitcoin becomes particularly interesting. 1 terabyte of blocks is impossible. So let's read what they said on this presentation. Was really important to me because when I went there, of course, I was like, everybody, when they meet Bitcoin, they are there to fix it, right? I've just learned a Bitcoin, I'm here to fix it. Why 10 minutes? Come on, Satoshi, just do 1 second. I want 1 proof of work every second. Why 1 megabyte? Fees, there is no space for everybody. Just do 1 terabyte. And then you get this bat tube. But when you get one side with this bat tube, then you say, wait. Let's just do 1 single transaction. So 1 proof of work must include just 1 transaction, and this might happen every 2 days. So this is very, very decentralized. Sure, but then you have the other failure. Nobody can enter the block. So this bat tube is very nice, and basically they are saying left side failure, so very, very small blocks. Key failure, a failure to store your key. 1 TX per block. Let's assume the block is every 10 minutes. So this is the same trade-off. If you are doing time or space, is the same. If you do smaller blocks but more frequent, or if you do larger blocks but less frequent, it's the same bandwidth, basically, the same throughput. So 1 transaction per block every 10 minutes means 100 transactions per day. The block size increases, the blockchains, this is wrong, the blockchain increases by 50 megabytes per year. A full blockchain can be verified on your phone. That's great. So every cheap phone can verify the system. So you can receive money trustlessly. But there are about 10 large institutions that will have the private keys to the UTXO set, to the coins, and everybody else will just have to have a bank account with them, some credit with them, some Bitcoin denominated credit. So Coinbase, ChangeTip, Bank of America, BNY Mellon, they will move Bitcoins around, and you will just open an account trusting them. We go back to the banking scenario, to the unit of account scenario where somebody else is keeping credit for you. This is not good. It's a failure, right? Because we don't want digital banknotes. We want digital collectibles that everybody can verify for themselves. This will become digital cash in the sense of being digital banknote, which is used by somebody else. So ironically, very, very small blocks will be digital cash. Now, on the other hand, very, very large blocks, which ironically is what is being advocated by people that are supporting a coin called Bitcoin Cash, but it's the opposite of cash. In the other side of the spectrum, you have you basically go to how much. I don't see exactly how large is the block, but the block is very large. So it means that all 7 billion people. It's funny because Taj is writing 7 giga human, giga human. So 7 billion people can use Bitcoin many times a day for any transaction. That's great. Everybody can hold keys and everybody can use Bitcoin. Everybody has their own private keys on their phone, but we have around 50 exabyte per year of expansion. 50 exabyte. Now, we will explain that you can prune the node, so it's not a problem of storage. You don't have to store 50 exabyte, but you have to download and verify. Basically, I tell you now. What you need, when you download the chain from Genesis, you have to check that the transaction were correct. It means that you have to download the transaction, check the hash, and now you can throw the transaction away. So people, the users of the system are not really forced to store the blockchain forever, but they just have to store the current UTXO, the current coin set, and then they have to download all the transactions, build the current state, and then they can throw the transactions away. Of course, if you lose the state because your computer is broken, then you have to re-download everything from from 2009. Every time you want to reach the current state of the system, you have to re-download the full blockchain. So Taj is saying, in order to receive money trustlessly, you don't have to store 50 exabyte, but you have to download 50 exabyte every time you join the system. And of course, that means that if you have, for example, 1 terabyte of blocks, that's the other problem. In 10 minutes, all the nodes of the world must be able to download 1 terabyte before 10 minutes. Otherwise, by the time they, on average, they download one, there is already the second coming on. And that creates a lot of orphans, which is bad. SPV proofs are basically, SPV is the idea of Satoshi that you can not check for exclusion, but only check for inclusion. So don't download the transaction, just download the Merkle roots, which are called the headers of the block, and just check the proof of work, the difficulty, and the inclusion, and then just trust the miners that are behaving correctly. Why can you trust the miners? Because if at least one miner is honest and they see that there is a mistake, there is inflation, there is a theft, they can send you. But as I said last time, this doesn't work because if any troll can just send you signals that every block is wrong, and the only way you have to check is to download every block again. So we're back to the start. In this case, only about 10 large institutions can store and verify the blockchain. This is wrong. It's not really store. Only 10 large institutions can download and verify the blockchain. They don't need to store it necessarily. While you have a lot of keys, only Amazon, Visa, Google, Bank of America, Union Pay are the only one that has the blockchain. So when you receive money, you have to ask them, did I receive money or not? So the right side of the bat tube is going back basically to a central mint or a few central mints. You have to trust. It's like trusting Alfine. In this case, but without the secure element. So in this case, you're best trusting Google. The left side of the things is just trusting a bank. Now, big blockers, so the guys that want to go in this direction, they are arguing, this is a good argument actually, a mint is better than a bank. And if you go back to this, you could agree, like a mint is better than a bank, right? It's more on the left. That's fine. The problem is that the debate was such that actually we found a neat solution to go on the left side of the bathtub and still have great Bitcoin UX. How? By introducing second layers. Before getting to second layers, we can also make a break, but let me just introduce the last a last comment on this. Uh, this is the problem of Bitcoin. When Satoshi proposed Bitcoin, there was one guy, James A. Donald. By the way, if you go on the Satoshi in the Nakamoto Institute page, I already showed the Nakamoto Institute website. You go there. There's also, well, let's do it like now before the break.
Maybe a couple of questions before the break.
Yeah, we'll also take that. So let's go to Satoshi Nakamoto Institute, the complete Satoshi, and here so there's the white paper, of course, the forum, the code, the quotes. There's emails. This is the first email, Bitcoin peer-to-peer cash paper, October 31, spooky Halloween 2008. And then there's Satoshi Nakamoto. Yeah, I've been working on a new electronic cash system that's fully peer-to-peer with no trusted third party. Take a look. And then there is thread, and then there is James A. Donald. So November 2, in a couple of days, is the first guy to even care. And he says, we very, very much need such a system. But the way I understand your proposal, it does not seem to scale to the required size. That was clear after 3 days. For transferable proof of work tokens to have value, they must have monetary value. To have monetary value, they must be transferred within a very large network, for example, a file trading network akin to BitTorrent. To detect and reject double spending event in a timely manner, one must have most past transactions of the coins in the transaction, actually all, which naively implemented requires each peer to have most past transaction. The way Satoshi implemented is all past transaction, or most past transaction that occurred recently, not even all of them. If hundreds of millions of people are doing transaction, that is a lot of bandwidth. Each must know all, or a substantial part thereof. So this is broken. Like as Satoshi Nakamoto said, no, don't worry, I have SPV, but he was wrong. And Satoshi realized that he was wrong, and he started to work on something called a payment channel by the end of 2009. But in 2008, he was confidently wrong. Like, no, we can fix this. And the problem that James A. Donald discovered, it would be great to invite James at the conference. I don't know if I hope he's alive and well. Let's find James for the next forum. So the problem with this BatTube is that it's a problem of global consensus. It's actually this problem here. In a newspaper, you are just trusting. In the newspaper, you are trusting the newspapers already because you're already trusting them for the date. So let's just trust them for exclusion as well. Let's trust them that they don't put competing. Actually, no, in guard time, nobody was checking for double spending, so you don't care. But in Bitcoin, you do care for double spending. So you need a proof of exclusion. You don't need a proof of existent. You need a proof of not existent of competitor transaction. So you need all the transaction, which is the problem of global consensus. In order for this Bitcoin to work, you need all the users to download all the transactions forever. This is very bad for three things. One, this BatTube, basically, number of transactions per block. Very few, and then spending become trusted. Very many, and then receiving becomes trusted. That's bad. Second problem, it's timing. Many transactions per second, so many blocks per second or per minute means a lot of orphan rates, but good UX. Fewer blocks per second means terrible UX, but decentralization. Third problem, privacy. As we said here, you can use guard time privately because you don't publish your documents. You publish just your hash of the document. But here, unfortunately, you publish all the document, which is the transaction. Sure, there is not your name in the transaction, but there is a public key which connects with other public key. And if one of your public key is leaked for some reason, then the others can be probabilistically de-anonymized. And also there are all the amounts, which can allow people to do amount correlation and stuff like that, which is nasty. So you have privacy, time scalability, people scalability. Plus you have some problem of censorship resistance because miners could be paid to censor your transaction. In guard time, the Washington Post cannot really censor your documents, because the Washington Post will just receive a hash. They don't know your document. So you can timestamp your document and nobody can stop you. But in Bitcoin, the miners, they see the transaction. They don't know your name. But if they don't like the public key because it was already used by somebody or whatever, or whatever reason, they can censor it. So it will be better not to have a public global consensus. We need it to have a double spending prevention. We need it. But it would be better not to have it. Most of the buzz was, let's have blockchain without Bitcoin. The reality is that we need Bitcoin without the blockchain, if possible, whenever possible. Now, it turns out it's not entirely possible to get rid of the blockchain. But what I want to stress to you is blockchain bad. Blockchain necessary evil. We need it, but we don't want it. Bad for privacy, bad for number of people, bad for time of transaction, bad for censorship. Bad blockchain. But we need it. So can we have a minimal use of the blockchain? And that's the next part of the lecture. Now we take a few questions.
At the beginning of the lecture, it's just a curiosity actually. You mentioned with the inputs and outputs, you remember, and the fees, no?
Yes.
Yeah, if you can take it. My question is, there is no address on the fee,
No,
right?
correct.
So how technically these fees currently go to the miner?
That's a very good question. Let's see how it turns. If you go to Learn Me a Bitcoin, you can actually see the structure of a transaction and study it, which is it's a very good way to check it. But basically, the idea is that. Let's do this. So in a block, in a block there is a header with the version number, the hash of the previous block, the Merkle root of all the transaction, the timestamping. These are bits to signal stuff, the nonce to find the proof of stake, that doesn't matter. Then you have the transaction. You have n transactions. The first transaction is always called a Coinbase. Let's also do it on this. The first transaction is called a Coinbase. Where is this Coinbase? Wait. Where does mempool puts the Coinbase? Let's do maybe blockstream.info. So we take the last block, which arrived a few minutes ago. These blocks, okay. This block has many transactions, 2,610 transactions, this block. The second one is one input, one output. The third one is 1, 2, 3, 4, 5, 6 input and 2 output, okay, and so on. But the first one is special. The first one has no input and only outputs. So when a miner discovers a proof of work, they will include all the transaction. The first one is a special one that we call Coinbase, where you can create out of thin air all the output that you want, but the amount must be the inflation subsidy of the high halving epoch plus the fees of all the other transactions that you collected. So your Bitcoin node, when you receive a block, they will check that the Coinbase will have some outputs. The sum of the outputs of the Coinbase must be the differences between all the outputs and the inputs of every other transaction, which is the fees, plus the right amount of subsidy for this halving epoch, which is like 5 billion, 2.5, and so on, depending on the halving. So, this miner decided to send all the money in the Coinbase to his own address. So when I say Alice sends assigns or issues the proof of work to herself, that means that she puts her public key inside the proof of work. In this case, when you have to collect other people's transaction, you put all the transaction plus one, which is a special one, which is the first one, which includes whatever others you want. If we are doing mining together, we can put two outputs, one for me, one for you. That's how it works on Ocean, for example. Every big miner in Ocean will put their own address as an output. And you can do even more complicated things, but very good question.
And another one is, could you elaborate your take why Satoshi chose to cut in half block reward every 2,000, 10,000 blocks instead of, for example, steadily decrease block reward block by block?
Yeah. So so why cut in half? So let's start. I think based on logics and based on a very few comments by Satoshi, which basically boiled down to it was simple. So what he did was probably first think about the 5 minutes, then think about I think this is my hypothesis, 5 minutes for block propagation, then 1 megabyte for block propagation of 5 minutes. Then he was thinking halving to incentivize the fees over the reward, because otherwise you can have censorship. Halving, he says 4 years. And then he said difficulty adjustment. When do we do it? And he said 2 weeks on average, because you need to have adjustment on time. Now, why not every blocks? Mathematically, it's very elegant, because you have instead of this ugly thing, you have a smooth one. It would be more elegant. Implementation-wise, it's trickier actually. Just cutting in half every 40. So doing continuously is mathematically and computer science-wise a little bit more tricky. So he just went for the simple. So now you have discontinuity. If you cannot have every block, if you don't change the supply every 10 minutes, when do you change it? And he just selected, he basically just choose to do it as a presidential change, basically, like an epoch. So it was simpler this way, I think. We could have a Bitcoin that changes gradually. Peter Todd's idea is that halving eventually will become traumatic for miners, and it would have been better to do something smooth instead. But he didn't.
Another one?
There is another one from Masari. Surely this has already been discussed, but it is possible to replace SHA 256 with other hash functions, such as those from the SHA-3 family. The SHA-2 family was introduced as a quick fix after the discovery of SHA-1 vulnerability, increasing the digest length, but still maintaining the same underlying architecture of SHA-1.
Yeah, so secure hash algorithm 1 had a vulnerability. So actually the NSA, so not really the best friends of Bitcoin, but sometimes, so even technology that can be used against the government can be created by the government, because governments also use technologies against the government, against other governments. So like many parts of the US military are behind the creators on the internet. So now the governments of the world, they want to shut down the internet in Iran, they want to shut down the internet in Turkey, they shut down the internet in North Korea, they control the internet in China and in the UK. So there's a lot of internet as an enemy of the government. But during the Cold War, the government needed a communication network that could resist atomic bombs. So they created the internet with ARPANET and so on. And Tor is actually sustained by the US government, because they need communication privately over the internet, which cannot be easily intercepted by the enemies of the government. So every government, well, almost every government has other governments to fight. So the fights against the government is not the solitary fights of subjects. It's also fights for the governments. So this is a case for cryptography as well. Government often try to kill cryptography or to corrupt cryptography or to break cryptography, but they also try to create good cryptography. And so they created also the SHA-2 family, including the 256. Then they created a better algorithm, which is SHA-3. The point why Satoshi, so will it be possible to upgrade the algorithm model? In theory, yes. So let's do it now. There are two ways to change consensus. Let's do it now very quickly, and then I can do it again. There are two ways to change consensus rules. One is we restrict the rules of consensus. So we keep all the rules and we just put new rules. This is like a group of vegetarian people. So let's say that we are a group of vegetarian friends in California, and now that's not trendy enough, and we want to become vegan. Now we are introducing a new rule, which is basically no milk for you and no eggs. This is called a soft fork. I will explain a bit why, but it's a restriction of the rules. Instead, removing one rule, like okay, guys, our blood tests are terrible. Let's go back to at least eat fish. And that's a breaking of one of the rules. You are basically going from vegetarian to pescatarian. And in this case, you have what we call a hard fork. Terminology is a little bit confusing. I will explain to you another time why this is a terminology. And the point is that in order to change the fundamental rules of Bitcoin, like this one, or this one, or the kind of signatures, or the kind of proof of work, including SHA-2 256, that requires a big change in the rules. Now, if you want to do a soft fork, that requires at least a strong economic majority. What does it mean, economic majority? It means most of the economy, very ill-defined concept, and a majority of the miners, or the hash rate. If you want to actually do a hard fork, so to break a rule, it requires basically everybody to upgrade. Otherwise, people that just set up Bitcoin and go away, don't care anymore, and they come back. If they don't upgrade, they cannot use Bitcoin anymore because they reject transactions that are valid now as invalid. So hard forks are something very traumatic that should be minimized because they force every user to agree. Soft fork, they are less traumatic, but still they are tricky. And so changing something like changing something like mining algorithm to move from SHA-2 to SHA-3 will be an hard fork. Unlikely to happen. And even if the point is that even when hash function gets broken, usually that breaks the double pre-image resistance, which is not really needed here. And even if you weaken the pre-image resistance, mining is not a security challenge. It's a collision challenge. People want to partially break hash. They're just competing to find a partial collision. So even if the function becomes weaker, that just means that it's easier to find an entire collision eventually. But that just means like a super high difficulty. So in a way, it's unlikely that any vulnerability, so many vulnerability that will be fatal in other application of hash will just be another mining adjustment in Bitcoin. So very hard to replace SHA-2 with SHA-3. In case it's very necessary, we could probably add a SHA-3 or something else, or script or whatever, on top of SHA-2. That is possible. To add a new proof of work on top of the old one, so now you need the old ASIC plus a new something else. This is a soft fork, and this is easier to do. For example, in case of terrible centralization of miners, in which the governments just size up all the miners of the earth and they just censor blocks forever, maybe you want to change the proof of work to add a new optic proof of work to destroy the mining industry. If we want to do that, we need the super majority of the economy to do that. And in order to do that, we also need probably to add, to keep which will not work in this case, but it's complicated. So the answer is, yes, we can. No, we probably won't. Yes?
So, just to be sure, in the previous example on Blockstream, the powder was the Bitcoin powder was 3 BTC.
Let's see, where is well, no, 3 BTC is not the powder, is the sum between the powder and the subsidy. The subsidy is not zero yet. Right now we are basically, around now, we are here. So it's not 5 Bitcoin, it's not 2.5, it's not 1.25, 6, basically, sorry, no, we are 3, right? We are here.
Okay.
So now you get 3.125 every block. So this is 3.125. So there is 0.03 as a dust. In mempool space, it's a little bit easier to see the powder. It's this. But it's harder to see the Coinbase. I don't know where. does mempool show the Coinbase? This is a strange graphic. Sorry?
This is the transaction.
Yeah, and the transaction. That's sorry, obviously. Thank you. Of course, the transaction shows the fees, and these show the Coinbase. This Coinbase. Let's open the Coinbase. Let's see how they. Okay, nice. This is a Coinbase. So you see, there's no input here. It's starting from. So this is collecting the inflation plus the fees. What is this? Yeah, this is strange. That's broken, right? Okay. Yeah, should be connected. Yeah. So just rendering. No. Bug. Found it. Well, but still it should be connected.
But it's zero BTC.
Zero. No, it's not bugged. It's right.
Well, anyway. Okay. So I think I answered. Let's break for 10 minutes and let's go back. Well, let's say 15. Come on. We can make it. In 1 hour, we can make the rest. We go a little bit faster. So let's be timely back here at 12 at noon Lugano time. 15 minutes to get a coffee.
Anyone need to go to the bathroom?
PC. Ok, perfetto. Grazie.
Aspetta solo un secondo.
Sì.
Yes, unmuted. Appena mi dà conferma cambio, iniziato, partiamo.
And we are back. Welcome back. Today you also had the luxury of a break. This is almost unprecedented for my lectures. I hope I convinced you by this time that global consensus is the enemy, the necessary evil. So where do we go from here? We go left, and we have basically banks. We go right, and we have mints. But if we go left a little bit leftish and we add a trick, maybe we have a solution. And this solution was presented by the same guy that was presented the Batube. And the solution is the Lightning Network. I call it network of Lightning because I'm crazy and I want to have like store of value, proof of work, and all this stuff like this. So let's, at the beginning of every chapter, let's take a step back and take a detour on something apparently unrelated. That something apparently unrelated is the concept of smart contracts. The term smart contracts was coined by, again, Nick Szabo. By the way, Nick Szabo, even if you block me, he's an incredible polymath, and you should check out what he wrote. I already gave to you as an assignment reading Shelling Out about the history of money. But if you check out his blog, which is called Unenumerated, you will see that he is covering everything from economics to cryptography to contract theory to sociology to pottery and whatever. Is a real polymath. And he was basically thinking that together with the electronic cash system, so if we go back from around here, from digital credit to digital cash based on private keys and public keys with eCash, we want to keep all the convenience, the fact that we can send the money across long distances very fast. Okay, that's very convenient. And we can store money with just one secret number in our mind. That's very convenient, even if it's also complex, but it's also convenient. But there is another conveniency of digital system, which is programmability. A bank account can be programmed to pay every 10 days your bill, which is a nice feature. You cannot have that with shells or coins. You cannot have magical coins that will just self-move to the recipient. Not even with physical banknotes. You don't have that. You just have that with digital credits. You have subscriptions, automatic payments. You also have in companies right now, you have conjoint accounts with disjoint or conjoint signatures. So you have a bank account that just one can spend, or two together, or three together, or 1 + 5, or all these conditions. And you have a bank account, you can have a trust, which cannot be moved by the hair for 10 years, and then it can. Or you cannot have a piece of gold that cannot move for 10 years, and then it can. You cannot have a piece of gold or a coin or a banknote that cannot be transferred for 10 years, and then it can, or that can only be transferred by two people together. Now, if you have a bank, you can have the bank giving you back the money to some conditions. So I will redeem you the banknotes only if you come in 2 or 3 or after 10 years. Yes, but while the market, the secondary market, is circulating the note, the banknote, the bearer instrument, this instrument is not encumbered by any specific condition. I have it, you have it. There is no conjoint signature, there is no disjoint signature, there is no time lock, there is nothing. So Nick Szabo was saying, if we're moving from digital credits to digital cash, why give up the programmability of digital credit? That's actually a feature we want to keep. Of course, programmability with identity is bad because I can program your life by programming your money. But programmability with strong privacy and with cash, anonymous bearer instruments, that's fine, let's keep it. So Nick Szabo said we could we could do even more. if we remove the banks, if we remove the purely identity-based system from the loop, we can have very complex system where computers, instead of central authorities, will decide the condition. And we can make complex contracts where you can have escrows, future contracts, any kind of stuff, which is just depending on computer code. When Szabo invented the smart contracts as a concept, reusable proof of work was not around yet. We were discussing mostly eCash. So it was at this phase of the diagram, the key phase of the diagram. And so smart contracts were an idea. Alfini was aware and was imagining to include smart contracts in reusable proof of work. He didn't. Wei Dai was aware and he was imagining to include smart contracts in his proof of stake system called B-Money. Nick Szabo, of course, wanted to include smart contracts into BitGold. It was a big part of what he wanted to do. And Satoshi Nakamoto did include smart contracts. You can see here the picture of the language that he included. The language is very general, even if the most important primitives are three. One is multi-signature. So this coin can only move with one signature or two, or 1 out of 2, or 3 out of 5, or this plus one of these other 6, or every combination of conjoint and disjoint signature. That's one. Time locks. This UTXO, this coin, cannot move until 5 years are passed from the creation, or until that specific time in the future. Time lock. Hash lock, which is a little bit in between. This coin can only move if you reveal a pre-image of an hash. These are the big three primitives where you can build mostly every kind of contract you can imagine financially. Of course, you cannot play Doom on these kind of contracts, but you can do a lot of stuff. Satoshi did create a programming language, which is called Script, which is very flexible, is not Turing complete, is not, you cannot play Doom on Script. And there is intentionally, the idea of Satoshi was, I don't want a general programming language. Satoshi already had a general programming language. It was called C++. You may like it or not. That was he used to program this. So he had a Turing-complete general languages. What he wanted now was to create a sub-language, a dialect inside the system that was not complete, and it was just a domain-specific and allowing you to do transactions. So these were the big things were sign with keys, verify keys, hash stuff, check signatures, aggregated or disjoint, in combination, check hashes and pre-images, and just wait for lock times, relative or absolute. That's basically it. He said that in order to stay on the safe side, he started a bit more flexible, but then he changed his mind because he started to see that some combination of code created infinite loops, for example. And that's bad because it's a little bit like the same problem of the Bathtube. If you have a block, which is just 1 megabyte, but when you download it, is 1 megabyte. But when you run it to check if all the operations are correct, it's taking 2 years. You have the same problems of a big block. You can have a small block, which is incredibly costly to evaluate time-wise, which is as bad as a big block for everything that we discussed before. So you don't want that. So Satoshi wanted a smart contract language that was highly deterministic, no loops, no unpredictable stuff, easy to audit before running it. So he created it already limited, and then he limited it even more, and he deactivated most of the opcodes. So let's check on Learn Me Bitcoin again. You go here and you do script. Of course, if you are here for the business track, you just check it out very quickly. If you are here for the development software track, go to this page and really dive into that. That's an assignment. This is a very great to explain script. It's a mini programming language which will do stuff like this. For example, it's a stack-based. So if you are not into programming, I will not explain what it means, but basically it's concatenative, stack-based, a little bit like Forth or PostScript. And it means that there is this stack and there is this queue. You take element from the queue, and you put it on the stack, and then you evaluate the elements on the stack, and you do stuff with the stack. In this case, for example, this is a spending of a transaction. There is one signature, there is one key, there is one duplication of code which duplicates the key, so now you have double the key. There is an hash function that will hash the last of the two keys. There is an equal verify. There is the hash that you want to verify. There is an equal verify that checks if the hash that you are checking for is equal to the hash that you just produced with the key that you multiplicated. And then there is the check signature, which will check if the key that you just verified corresponds to the hash, corresponds to the signature of the actual message, which is the transaction itself. Again, if you're not a developer, it's not super important that you get into details about that, but if you are a developer, you need to exactly understand what's happening here. Now, a few things happening with smart contracts. The first one is that people, especially in shitcoins, well, you have to know that, as I told you, the first reaction to Bitcoin is, I just learned about Bitcoin, I'm here to fix it. So some people saw Bitcoin and they say 10 minutes block time. That's a lot. That's bad UX. Let's just do 1 minute or 1 second. And then now you have a Litecoin or Dogecoin or whatever. Of course, there is a cost, total centralization of mining. SHA-2, well, not only is like it was a quick fix on SHA-1, but also SHA-2 is something where people started to optimize it with GPUs. I miss the old times in which we could use GPUs instead of CPUs. So let's do another algorithm, which is GPU resistance. And then, of course, they will optimize it for GPU anyway. And then let's do something which is FPGA resistant. And then somebody will find an FPGA. And so on and so forth. And now you have all this kind of different proof of work algorithm. Let's do something. So there is like one of the biggest altcoins in 2011 was Prime Coin. Instead of doing SHA, let's do finding new prime numbers as a proof of work, because it's useful to society at least. The problem is that it must not be useful, because in order for proof of work to work, you have to show that somebody is sacrificing energy. So you have to have a sacrifice, something that is given up, a natural resource which is consumed in order to prove that you cannot undo history and you cannot inflate the supply. If you do a work which is usable for something else, you are reducing the cost to reorg the chain, of course. So you are taking out that work. So it doesn't work. So many things have been tried. Proof of stake has been tried, doesn't work unless you centralize, and then it works because it's centralized. Useful proof of work, it's a nonsense in this context. As very large blocks, very small blocks, very fast blocks, very slow blocks. Everything you try to change, you will have an effect. Another change was, why having this? Let's do a contract language which is general purpose and completely Turing complete. Even nothing in reality is Turing complete, but assuming infinite resources is Turing complete, very flexible. And let's make it similar to JavaScript as a high-level language, so that web developer can code complex smart contracts. And now you have something like Ethereum coming up and stuff like that. But the idea of Satoshi was not flexibility. Actually, he created something not flexible, and then he reduced the flexibility even more for the sake of security. Because the point is, with these primitives, which are basically multisig and time, you can do basically everything. Also because most of the complex contracts you can imagine, let's say escrow or derivative contracts, they still require some data outside of the system. So if you require data from outside, you will require a trusted source of the data, an oracle. If there is an oracle, you don't need complex data. You can just have a signature of the oracle, and that's basically can emulate everything. And if you really need complex situation, you can still go back to the idea of Al-Finney to have a trusted computing chip that will keep a key and do the oracle with whatever language you want. So HSMs are already solutions. So most of these smart contract ideas being completely redundant. The main feature was market hype, because now you had front-end JavaScript developers that could use their JavaScript skills to come out with very convoluted schemes. But also this making contracts on chain, like in script, is also bad because it goes back to this problem. It means that all the contracts are not private because they're there for everybody to see, and you don't want, when you move, you don't want to leave the public know about your financial contracts. That's against any sane rule of financial privacy. And you don't want to have miners selectively censor or slow down or speed up some contracts, because otherwise you have what is called MEV or MEVIL, which is basically miners. They check the complex contracts, they take a position in the financial contracts, and now they slow transaction down or they speed them up in order to win. And it's what happens if you have complex contract on chain. And of course, no privacy, no scalability, and no resistance to embed mining incentives. So Satoshi kept this intentionally small, and he made it even smaller. And and you can check different kinds of smart contract. There was the main change in Bitcoin was, let's just take this detour, but I will try to be very quick with this. Basically, the very first type of address in Bitcoin, if I have to send you money, the very first idea was pay to IP. Pay to IP. I pay to, so when Satoshi sent Satoshis to Alfine after a few weeks from the start of Bitcoin, Alfine sent an IP address to Satoshi. The Bitcoin software of Satoshi connected with the Bitcoin software of Alfine via IP address, and they negotiated a public key. So that was pay to public key. But then Satoshi changed his mind because that was very bad security, because IP is not secure. You have man-in-the-middle attacks, bad privacy because IPs are usually connected to your name. So that was very dangerous, because if it was Alfini paying Satoshi, not otherwise, we will know the IP of Satoshi, which is also pretty bad. So not private, not secure. So basically, he moved to pay to public key hash. Instead of giving me your IP, please, Alfini, give me your public key. And since the public key is large and I don't need it, just give me the hash of the public key. These are the address starting with 1, etc., etc., the very old address. But then the problem with this is that in order to do a smart contract, you cannot actually pay to a public key hash if you want to do a smart contract, because you have to. So let's say that Alfini is saying, this is the hash of my public key, but I also want to make a multi-sig with my wife. So you need to construct the smart contract, either this hash of a public key or this hash of a public key. So in order to make it simpler and also more scalable and more private, developers, actually Satoshi was gone already, Gavin Andreessen came out with another idea that was pay to script hash instead of public key hash. P to S H. Pay to script hash. So these are the addresses starting with 3 something. These addresses are such that instead of giving you a key or a hash of a key, I take the whole contract, including the keys, and then I give you the hash of the contract. But as you learn from guard time, hashing big stuff is not a great idea. The best thing is to Merkelize stuff. You should take small pieces and only publish the Merkle root, not the hash, but the Merkle root. So you can reveal specific single parts. So we move to something called Taproot, which there is a lot to say about Taproot, including the difference between CDSA and Schnorr, a lot of things to say. But basically, Taproot is almost pay to Merkle root, script Merkle root, let's say. Not really, but almost. So instead of taking the script and hashing it, you take the script and you make the Merkle tree of all the pieces of the script. So when you spend, you only reveal the parts that you will need. So this is very good privacy, very good scalability. And these are the address starting with B, C, etc., etc. And these are case insensitive. Actually, that's not entirely true, because these already started with SegWit, but segregated witness is just a way in which developers moved the signature in other place of the transaction. But this is not important if you're doing the business track. You will see more details when you enter a developer track. So the first kind of address was just the IP that give you the public key. Then the hash of the public key, then the hash of the smart contract, then the Merkle tree of the smart contract, which is Taproot basically. And this is the most innovative kind of address. At the end of this lecture, hopefully, you will agree with me that now we're going to pay to Lightning invoice, which is something completely different, possibly something like Bolt 12. But even to pay on chain, eventually we will not use addresses anymore. And this is kind of getting to a better version of this. So we're going back. We are back. But this time it's safe, no man in the middle, good privacy. But this is the coolest idea. So you can negotiate any kind of payment protocol, refunds, split payment, reusable keys. You can do real smart contracts in commerce this way, escrow, a lot of different stuff. Now, let's go back to this. So you have smart contracts. You can use I'm very late. You can use smart contract to do many things. But in order to fix, you can use smart contract again to do inheritance. So this is the money that I can spend now, and my children, they can only spend it in 3 years if I'm not here anymore. You can do escrow. I pay you only if the judge co-sign. So the judge cannot get away with the money, but it can only make the money come to you or back to me. So you can do many, many, many things. But two of these things are very important. The first one is called the Lightning channel, or a Dria pool channel, because it's coming from Tadeusz Dria, which was the Batuk guy, and Joseph Poon. Lightning channel, the reason it's called Lightning will be clear in the next slide. But let's call it just a channel. Satoshi had an idea of how to create a channel. Then a guy named Spielman created the first kind of operational channel. Then Peter Todd and others tried to improve on it. And then finally, Christian Decker and Tadeusz Dria and Joseph Poon independently rediscovered another way. What is a channel? Again, the first example was created by Satoshi himself. Satoshi said, if we want to trade between two parties many, many times, it's a waste to write on the blockchain. So if we want to trade many times, instead of writing on the blockchain, let's just write once that we are putting our money together in a co-signed address. So there is an address that in order to move it, it requires my signature plus your signature. Now, I pre-sign a transaction that gives you your money back. And you pre-sign a transaction that gives me my money back. You give me the pre-signed transaction, I keep it. I give you the pre-signed transaction, you keep it. Now, at any moment, I can go back on chain with my money, and you can go back on chain with your money. Now, the smart thing is that off chain, without anybody knowing it, we can just give you another percent transaction, which increases your share and decreases my share. So I'm paying you off chain. And you can give me another transaction that increases your share and decreases my share. And well, that's the same. I'm still paying you. But if it decreases your share, increases my share, you are paying me. Now, this, you don't need a lot of smart contracts for this. It's just a 2 of 2 multisig. The problem is that you have a trivial form of double spending. We can make, so I put 1 Bitcoin, you put 1 Bitcoin in the contract. There's 2 Bitcoin. In any time, I can go back with mine, and you can go back with yours. If I want to pay you, I create a new transaction that gives you 1.5 and only 5 to me. So I am paying you 0.5. That's great. But you cannot trust me because I can still go on chain with the old transaction. It's still valid. It's still there. It's still off chain. And if it goes on chain, it's valid. So you need a lot of tricks, time locks, hash locks, other things in order to make it so that one party can only go on chain with the last valid state. So you're moving the double spending problem off chain. It's complex. I will not explain to you how a Spielman channel works, a Decker, a Wattenhofer channel works, or a Dria Poon channel works. If you are in for the developer tracks, you will learn it, especially if you focus on Lightning in your assignment. And anyway, I will suggest you at the end a resource to learn Lightning very, very well. But there are different kind of channels. But the point of a channel is that the participants of the channel typically are very few, like trivially 2. You can make a channel with 3. To do it already with 5 would be very, very complicated. So typically it's 2 people. And these channels, you create it. Now you move the money back and forth, back and forth, back and forth of chain. How many times you want. Good for privacy, good for scalability, good for censorship resistance. Consider that even if the miners don't mine any block, as long as both of you cannot go on chain, you can keep trading. So the miners are censoring the chain for 1 year, and you keep trading, and then you go back in 1 year. The only trick is if one of you is also the miner, then you can go on chain and I can't. But if we are both censored, we can keep trading. This channel can work even without the internet. If there is no internet, we keep trading, keep trading, keep trading. We don't have to go on chain. We don't need even the internet. We did an experiment when Russia first invaded Ukraine. We did a Lightning Network transactions in Ukraine without internet, and they were working. But of course, you cannot go on chain. When you need to go back on chain, you go back, you close the contract. So you open, you trade, you close. So this is a way to batch the transaction in time. So few people, typically 2, will batch the transactions over long times. Instead of sending 1,000 transactions on chain, they send 2 transactions, 1 to open, 1 to close, and they trade off chain, and then they go back. This is good because it means that they don't use the blockchain much, and the blockchain is the enemy. So that's very, very good. This was good, but there was always a problem. Because think about, for example, we are on this side of the bath tube, and on the left side, fees to get on chain are very, very high. So fees, let's say the fees to write a typical transaction are $1,000 equivalent of purchasing power. Okay, this is better because instead of spending $1,000 every day, I spend once to trade with somebody, then we trade for free, and then I spend $1,000 to close. Not only, if we do it very smart, maybe I don't spend $1,000. If we agree and we are there together and we don't try to screw each other up, we can just share 500, which is great. So it's less than 1,000 at least per person. But there's still a problem. First, if one of the 2 parties is unresponsive, the remaining party will have to pay the full 1,000. And even if they share, 1,000 divided by 2 is still 500. And even if this is kind of good, there's not so many transactions that you can do back and forth with a party. Usually, if you open a channel with your employer, the employer will just pay you. You usually don't pay your employer. And if you open a channel with a restaurant, you pay the restaurant. The restaurant very rarely pays you back. So eventually, the channel just depletes and you have to go on chain. And sometimes the other party will go offline and you have to go on chain. There will be a software problem, an hardware problem. You have to go on chain. You don't need the channel anymore because you're changing your restaurant. You have to go on chain. You're changing your employer. You have to go on chain. So it's good that you can batch over time, especially for repeated transaction back and forth. The channel is great, but it's not a solution. So much so that at the end of the paper about Lightning Network, they said, still, Bitcoin with channels, if we had to scale to all the people of the world, we will still have the battery problem. Is mitigating it a lot, especially for very symmetric commercial trades during very long times. That's mitigated, but it's not solved. So people were looking for something else. That's called coin. It has been this second part of the screen on your right has had many names. Was called the coin pool, dark pool, channel factory to a degree, many different ways. Timeout tree. Now, finally, there is a way to, we arrived to the point in which he made it to production, and the current cool name for it is an ark, like Noah's Ark, or the Covenant Ark, but I think it's more Noah. Actually, no, maybe it's more Covenant, because the first way, so the first idea to do this was that in order to do this, we have to change the rules of Bitcoin, to change script with a soft fork, to basically enforce something called a covenant, which is basically a condition not on the coin, but on the coin that will be created while spending this coin. So basically, condition remove one step. That's a covenant. You can emulate covenants with pre-signed transactions, but this was like asynchronous covenants. So ARC was created as an idea to do after we have a soft fork to introduce covenants in the scripted language. We never had this soft fork because we couldn't agree. And if we don't agree, if Bitcoiners don't all agree, there is no change in the protocol, which is a problem, but it's also a feature. It means that nobody can change the protocol in a bad way if we don't have a full agreement. And when we can discuss this a lot. So ARC was called ARC, I think, because of the covenant, probably. But then they realized they can do it without the covenant. And the company who is one of your teacher during this course, Marco Argentieri, Tiero, is the CEO of one of the two leading companies, which are the leading company. There's another one doing ARC implementation. Their company is called ARC Labs, and they are doing the implementation called Arcade. They are here. You can also visit their office next to it. They're also inside the proof of work space, and he will be your teacher and probably your assignment mentor. And they are the first to do covenants in production. ARCs in production. What is an ARC? I don't go into specifics again, but I would say that it's the opposite of a channel. The channel will batch transaction together of few parties, typically two, over very, very, very long times. The ARC will batch together transaction by many, many, many users over very, very, very short times. So instead of one transaction to open the channel among two, and then back and forth, back and forth, back and forth, and we close after 1 year, 2 years, 10 years. Instead, we still need for the block to arrive. But when one block hits, one transaction with one input and one output will settle the transaction among 1,000 users or 2,000 users or 10,000 users. So we have 10,000 transactions off-chain that gets confirmed inside one transaction with one input and one output. So channels are batching transaction in time. ARCs are batching transaction in space. They have different trade-offs. For example, ARCs don't fix the confirmation time problem. You still have to wait 10 minutes to be trustless in an ARC, or 40, or for a block, or for more blocks, or even more than one block. It depends on the cases. Before that, you are trusting somebody for doubles. You have a mint, basically. You are trusting a mint, like I will explain you a little bit more. In the payment channel, you still need confirmation, but just once. When the channel is confirmed, your payment is instant. So if you have a payment channel with a website and you want to buy something, you open the channel, you need to wait. Once the channel is open, you just pay immediately. You have instant confirmation. In ARC, you don't have that. You have to trust somebody for a while, and then after the block, you have the confirmation. But in the ARC, you can share the fees with thousands of users, which means that if you have $1,000 purchasing power equivalent today of fees on chain, with an ARC, you can share $1,000 among 1,000 users. So they all pay $1. And if one user goes away or are responsive or streaking, the other guys can just share, they can just divide 1,000 over, instead of 1,000, 999. So it's very good for scalability. But the thing I try to show with this slide is that they are not really alternative. They are mostly complementary. What I think will be the future, and Tiero agrees, I think most Latin people also agree, is, and we are not there yet, that's why it's exciting, because you can be part of a company that may do that. It's the merging between these two. It's not clear exactly how you can have ARC transactions that instead of just moving coin, they create channels among users of the ARC so they can have faster confirmation, or you can create channels among different ARCs so that at least the ARCs can trade over the channels, or you can do both, and you can do very complex stuff with channels and ARCs together. And we are not there yet to understand exactly what you can do, and it's great. If you have covenants, if we add covenants to the script of Bitcoin with a soft fork, so with the change of consensus, maybe eventually that will arrive, not sure, possibly not. If we do it, we can do the same things, just better. Because right now, the problem with this construct, both, is that you have to be online. So in order to create a channel with me, I have to be online. And if I go offline, the channel, you have to close it. And if I go online for too long, you can actually steal my money. And with ARC, it's even worse because you can steal my money even easier if I disappear for a while. It's slightly easier so if you are online, ARC is safe. I cannot steal your money. It's trustless. But if I go offline, you can steal my money in ARC, especially the coordinator. ARC is more centralized right now, but even the channels are centralized. So the first idea was, so channels are among few people. So the very first idea of channel, the one presented in the Lightning Network, well, no, let me go to the next slide first before I explain this. So my point here is we like channels, batching in time. We like arcs, batching in user space. We need both in some complex combination, which is not entirely clear yet. But this is basically the solution. But the solution was not there until now because arcs were not properly implemented on chain. No, I was saying, without covenants, both channels and arcs require interaction to be online. That creates privacy problem, usability problems, security problems for both. A little bit more for arc. ...2015, basically. So it was already a lot of time. In 2016, we had channels that could work, but we did not have working arcs, basically, or pools or timeout trees. So there was another idea. The idea was the idea of routing. So, and now I can draw on the whiteboard. So let's imagine that you want to trade with other people and you don't want to write on chain because it's very expensive because many users are on chain. And so now the on-chain cost is $1,000 per transaction on average. Of course, it depends on how big is the transaction. If the transaction is big, it takes up more block space. The fees on chain are not based on how much money you send, are based on how much big data-wise your transaction is. So a complex transaction with many inputs and many outputs and many long smart contracts, that's expensive. A simple transaction with one input, one output, and no smart contracts is cheap. If you send 1 million, it's the same as you send $1. Same. So that means that on-chain model is great for big amounts, is great because you still pay the same. Even if fees become $1,000, if you have to send 1 billion, $1,000 is a good fee to send 1 billion. If you want to buy coffee, except in Lugano, everywhere else, the coffee may be too cheap to justify an on-chain transaction. I just paid 5 francs, 0.25 or something like that. Crazy. It was a double. So it's basically, it's great if you can have a large amount and if you can wait time. But if you want to be fast or cheap, on-chain is terrible. So you want to open channels, but each one of us cannot open channel with everybody else because when you wake up in the morning, you will interact with your coffee place, with the lunch place, with the gas pump, with the supermarket, and then with your employee that will give you the wage. It's a lot of interaction. And if every user had to open a channel with everybody else, that will be that will not never scale. So with ARCs, that's mitigable, but without ARCs, that was terrible. So the Lightning Network developer came out with an idea, which actually gave the name to the Lightning Network, which was routing. The idea of routing was not new. Actually, this is a funny story. I've been scammed by Satoshi Nakamoto because there was a project called Ripple in 2006, 2004 actually. The project called Ripple, before Bitcoin, was the idea of routing credit. So Alice owes $3 to Bob. Bob owes $2 to Carl. We do that with public keys like eCash. So that now we do routing, and now basically we settle this debt, and now Alice will just have to give basically $2 to Carl instead, and the rest is settled. This routing of credit was called Ripple, was never really adopted because of some economic flaws, security flaws. But then Satoshi in 2009 wrote down on Bitcoin Talk Forum, Ripple is a great project, for example. And in 2014, I was in Amsterdam and I was a shitcoiner, and I was excited about many, many different coins. And there was this stand by guys with a coin called Ripple, and they convinced me to buy a coin because there was a Satoshi Nakamoto quote that Ripple was great, but it was not the same project. The project was shut down in 2007 and it was completely canceled. And then in 2012, new guys came out with the shitcoins, and they just used the name in order to inherit basically the authority of the name from Satoshi. So it was a scam, but it still exists and it's still big, this shitcoin. But it was not that. Anyway, routing, that means that I don't open a channel with everybody. I open a channel with 2 people, but then they open a channel with other 2 people. And with an average of 3 edges for vertex, you can basically map the entire economy. So what I need is a smart contract that says, I am Alice. I have to pay Zoe. In order to pay Zoe, I will do an atomic swap, where a special contract that says, I give you this signed transaction, dear Bob, but only if you prove that you did the same with Carl, and that will work only if Carl proves that he did the same with Daryl, and Daryl will do the same with Eve, and Eve will do the same with, well, whatever. You go until Zoe. So you chain these transactions in a way that it's atomic, meaning that either all of them go or nothing goes. And you do that with smart contracts, so you don't have to trust. You don't have to trust anybody in the process. And this is very important, and there are 2 characteristics that are in this slide. The first characteristic is multi-path. So the first characteristic is atomicity. You don't have to trust all the network. You want to pay Z, you just have to do the smart contract so that either the payment goes or it doesn't. The second characteristic is multi-path. So let's say that you have a channel with Bob, but you have to pay Zoe 3 Bitcoins, and your channel with Bob is only 2 Bitcoins, large. So what do? You open another channel? No. You have a channel with Hillary, which has a channel with Ivan. So you split 1 Bitcoin here, 2 Bitcoin here, because this channel is bigger, and you split and you rejoin. So this is why Lightning Network, because a payment starts and then branches off like this, like a tree, but actually not really, because then it will remerge, of course, in order to reach the same payment. So basically, Tadeusz Dria was calling the project Traffic Light, which is a very bad name. And so he was looking for online domain, and it is a network, so he's trying Traffic Light Network or the different names, and then he found Lightning Network. The domain was available, so well, actually, this looks like Lightning, so it's a Lightning Network. It just spreads around and joins again. The other characteristic is privacy. Each one in the process, actually, I have to add another point here, which is fees. Now I will do that. In the process, you have privacy in the sense that Carl doesn't know that he's routing a payment between Alice and Zoe. Carl only knows that he's routing from Bob to Daryl. He knows that Bob is asking him to pay Daryl, but he doesn't know that the payment to Daryl is conditioned to a payment to Eve, and he doesn't know that the payment to Bob is preconditioned by the payment from Alice. Alice knows that she's paying, of course. Zoe knows that she's getting paid, of course. Everybody in between doesn't know if the party next to them generated the transaction and received the transaction or just intermediated the transaction. Plus, there is something like which is called blinded paths, which is finally implemented in most Lightning wallets, which is great because it means that before, at the beginning of Lightning, if Alice had to pay Zoe, Zoe had to give to Alice all the path with also her public Lightning address, node address, which was very bad. The payer in Lightning had a great privacy. The receiver had a terrible privacy. To some degree, even worse than on-chain. The sender, way better than on-chain. So now with blinded path, we use cryptography to obfuscate the path as well, so that nobody knows where the money is going. There is another upgrade, which will be done. This is just for the technical people here. The smart contract used by the routing now is called HTLC, which means hash lock time locked contract. Instead, we are moving to PTLC, point time lock contract, where point is the point on an elliptic curve. So the better name would be, a simpler name would be key time lock contract instead of hash time lock contract. In hash time lock contract, all what happens very, very simply, I promise not to explain, but let's do it. Zoe will come up with a number. She will say, Alice, pay to the hash of this number. Alice will pay to the hash. Zoe will reveal the hash to Walter. We will reveal the hash, the revelation of, sorry, we reveal the pre-image. The pre-image will go to Eve, to Daryl, to Carl, to Bob, to Alice. But that's bad because that means that all these people are sharing the same secret, the same hash, the same pre-image, the same numbers. So that means if this was a Sybil attack, so if the same guy, Gustav, like a government, was pretending to do all these people, he will be able to reconstruct all the payment. Instead, with PTLC, privacy is even more because each step will have a different number because it's a signature and not an hash anymore. Changing the network is pretty hard. So PTLC is staying there for a while. I hope we need to change it before Lightning Network gets too much adopted. So I hope that Lightning Network adoption goes very badly for a while. Because let's not go too fast because this is way better. This doesn't need a change in Bitcoin rules, only a need in the Lightning Network rules. Now, does this scale? Well, it kind of scales because the point is that the thing here is that you know the Kevin Bacon rule. So there was this study of graph theory. You go on the internet database, intermovie database, IMDb, and you search for movies where you have Kevin Bacon, and then there are other actors that acted with Kevin Bacon, and actors that acted with the actors that acted with Kevin Bacon. And basically, you can connect all the actors of the world within 7 degrees of Kevin Bacon. So that means that if you have connections, if you want to pay somebody and people uses the Lightning Network, on average, you will just need 7 steps to get to the payment. So it's doable. It's always doable. Now, this is a little bit tricky because actors, in a movie, they're not just 2 actors usually. So that creates a lower Kevin Bacon coefficient. while in Lightning, you just have 2 users. So you have to assume that one single user will open enough channels. Also, Lightning is very bad for onboarding. For example, when nobody was using Bitcoin, on-chain fees were very, very low. What we used to do was, do you want to try Bitcoin? Let me send you $1. And you just write on chain, you waste space on chain, you don't care because it's empty, nobody uses it, and you just do it. But now, let's say that the fees are $100. What do? Can I just show you on Lightning? Well, not really. First, we have to open a channel. That's bad UX. And then if you want instant security, well, you can have it with Lightning, but first you have to open a channel. The nice thing is that Lightning, well, let me maybe get there in a few minutes, but so late. Let's try to do it. The trick here is that a Lightning network with both arcs and channels in different combination can actually probably scale to the entire requirement that we have. Of course, with covenants, it would be slightly better because it would be easier, but it could still probably make it. Now, is any problem solved if we do a Lightning network with arcs and with channels? Yes, except that people don't like to use Bitcoin with payments still. Why not? Because of volatility. This is light about the price of Bitcoin. I will not get into details, but basically we have at least 3 factors that change the price of Bitcoin a lot. One is demand. Demand is growing faster than with dollars or with gold, because dollars had a few decades to take hold, and they did it violently with conquest by the state, and gold had thousands of years to take hold. Bitcoin is still young, so demand is growing fast. How fast? This is a model which is called power law, which is basically, if you compare the price of Bitcoin, the logarithm of the price of Bitcoin with the logarithm of time, of number of days from the Genesis block, you find a very, very high correlation, which is basically the power to the time to the 6th. So price of Bitcoin is basically coefficient times number of days from the Genesis block at the power of 5.8 something, which is a confidence degree of more than 97%. The guy who discovered this, Giovanni Santostasi, is a physicist that works on gravitational wave detections. And in gravitational waves detection, you have to be very, very mindful of very, very small changes and a very, very, very hidden pattern in the noise. And he found this pattern, and it's very, very strong, something that any physicist will consider a super high signal. Now, this is not a magic trick to make money trading, because the noise on top of that is enough to completely cancel this pattern. Like this model will not have told you to sell at 120 before we got to 50,000 in a few days. So don't use it for trading. It will just get you wrecked. But if you just want to analyze the macro trend, and there is a reason for that in Santostasi's opinion, his opinion is that the spread of open source protocol tend to go with the power of 3 over time. That's also something you can see with the Internet protocol, with the Linux protocol and other things. And the value of a network tends to grow with the second power of the nodes, of course, because of the Metcalfe law. You remember all the diagonals of Metcalfe. The more nodes, you square, and you have the value of the network. So 3 times 2 goes 6. So there is a reason for this. It's just that out of his mind. But there is a reason, but you cannot use it for trading. On top of that, there is the inflation, of course. Even if Bitcoin stayed flat, gold doesn't have this rate, this power law of adoption. But gold still has an exponential growth because of the basement. This is the money supply inflation. So even if Bitcoin didn't have an adoption, it will still go up in nominal price. So will Bitcoin go to $1 million? Yes, for sure, but not because of the power law of adoption, because of the exponential decay in the value of $1 million. Eventually, $1 million will be worth so little that Bitcoin will be at $1 million. So there are 2 dynamics. The first dynamic now is stronger than the second. So if you do the Santostasi correlation between gold or with it US dollars, is the same. So inflation matters in a very long time, but in the last 10 years, inflation, even if it's high, is less strong than the adoption growth, the demand growth. And then there is the cycles. This is another interesting, this is basically a spiral view of the cycles. You can check it. His name is Rational Root. You can find him on Twitter. And this is a very nice cycle that shows you that most of the bottom and the peaks follow a 4-year cycles, which could be connected to halving, maybe. Could be that halving is just a trigger for the market to, you have like a very sudden supply shock. So maybe some miners refuse to sell to a lower price, and so that triggers. Or you just have news because of the halving, or there is a 4 years psychological cycle in the market, or the presidential election changes the head of the Fed, which changes the interest rates. So it could be many things, or all together. But so, and it could stop. So now the strongest thing we see is the power law. On top of that, it's very strong, these 4-year cycles, which may be connected to halving or to Fed dynamics or whatever. And on top of that, there is a background of inflation, slowly exponentially going on the background. It's a very large exponential curve, so you don't notice it yet. So this is great as a store of value, but it's not great if you want to receive money today at $125,000, and then you have to pay your provider in 3 days at $700. Well, actually, a little bit more. Let's say the next month is just $700. Sorry, $70,000. That's bad. People who have a lot of savings, so a Bitcoiner with a person with a lot of sets can just disregard this. I don't have sets, of course. I lost them all. I'm poor, but my cousin has sets. He doesn't care for inflation or for volatility. He doesn't. It doesn't matter. But if you run a business and you have a treasury of your company without a lot of, if you don't have a lot of buffer, you care for this. Most of the people in the world running businesses, they cannot afford a very large 4 years time horizon to settle. If you can survive 4 years with this kind of volatility, Bitcoin is great. If you can't, that's hard. So that's why Bitcoin commerce is not really taking off. Bitcoin as a store of value is taking off a lot. Bitcoin as a medium of exchange is hindered not just by technology, but mostly by this, in 2 ways. One is that if the price goes up, people will first spend the assets that will go down. If you go with dollars in Venezuela, people will first try to spend bolivars and then dollars. Of course, you spend the bad money first. So if you have dollars and Bitcoin and you understand Bitcoin, first you spend the dollars and then you spend Bitcoin. Now, this is bad, but this is somehow compensated by the fact that the merchant, if they understand Bitcoin, they want to receive Bitcoin and not dollars. So they will make you a discount like they do in Venezuela. If you pay with dollars, the merchant, so in Venezuela, paying with dollars is illegal. But if you pay the cop that is supposed to arrest you for paying for dollars in dollars, the cop will make you a discount on the bribe. So it's compensated to some degree. But still, there is a problem of volatility that requires a very large buffer in order for you to survive. So let's go to the last 2 chapters very fast in 10 minutes, and then maybe to the next lecture I will go through the last slides a little bit more, but I just want to finish for completeness. The first point is a point about legal arbitrage, and I will talk a little bit about BitTorrent. Let's ignore these 2. Well, the point is that blockchain and crypto just became meaningless buzzwords. So at a certain point, everything was a blockchain and everything is crypto, even if it's completely centralized. Just keep this in mind. Now think about BitTorrent. You had Netflix. Netflix gets shut down. So now you get BitTorrent. BitTorrent becomes 30% of the internet traffic. That's great. Now they cannot enforce intellectual property basically anymore. They give up. So now you have you have VKontakty, which is the Russian clone of Facebook. They just put every movie on. You just can see it all, or some random Russian site. Why? Well, it's not worth it to block it very much, because if you do block it, people will just go back to BitTorrent. And actually, it's better to use VKontakty. So at least on VKontakty, you can try to stop them from streaming child pornography or like terrible movies or like terrible footages or something. You can at least have some control. So you give up and say, okay, just go, because the alternative is worse. Something similar happened to digital assets. So Bitcoin is very free, and people were using Bitcoin a lot. But then a company, Tether, which is one of the two main sponsors of the Plan B initiative, and they started to think, well, basically, there was this exchange, Bitfinex. And moving Bitcoin was easy to Bitfinex and from Bitfinex. But moving fiat was hard because your bank account will have been closed if you send money to the Bitcoin exchange. So there was this guy that Brock Pierce that created this Tether company that was a dollar credit moving on the Bitcoin blockchain with a protocol called Omni, which was Mastercoin. A very complex story. Anyway, the owner of Bitfinex, he said, well, I need a way to get fiat in without people blocking me. So he bought this company that was just doing random stuff. And the idea was, you don't send your bank wire to my Bitcoin exchange. You send a Bitcoin wire to a company that gives you a voucher for $1. $1, $1. Now you move the voucher on chain to my exchange. The bank account will not close down this company because it's not trading, there's no leverage, there's no change of price, there's no volatility, no consumer protection. Just give $1. It's not an investment scheme. You don't have to regulate it with FINMA or the SEC. You give me $1, I give you $1 if you're lucky. So that's the investment scheme. Nobody can make money out of it. There is no investment regulation needed. And so the bank account is easy. And then people started to use it so much, and it was used by many exchanges because it was an open protocol. And then a lot of people started to send the dollar, getting the token, but never redeeming it, just like like it happened with fractional reserve. And Tether didn't do, apparently, there are many discussions about the audit, didn't do fractional reserve and just decided to keep full reserve. So it was 4 million, 4 billions, 40 billions, 400 billions. How do you keep full reserve of 400 billions? So the CFO of Bitfinex, he called the banks and he said, how are you keeping my money? And they say, well, we just buy treasury bills from the United States. It's the only liquid asset that tracks the dollars. So he said, well, I will do it myself. So when you send money to Tether, the money goes directly to the treasury in the US, and they give T-bills to Tether, which can liquidate it very fast. Now, my point is that this is like BitTorrent. Well, this is like vContacti, actually, and Bitcoin is like BitTorrent. So Tether doesn't just issue, Tether does many things because now the interest rates on T-bills, they increased a lot. So now Tether is the most paying company per employee in the history of mankind. So they have a lot of money. So they even sponsor this stuff because they have a lot of money. But the point is that they also issue another program, another asset, which is XAUT, which is basically a token of gold. Now, do you remember something? Like eCash, eGold, seems like the same thing. But it's not exactly the same thing. Because with eCash, you needed you could go to David Schum and tell him, I don't give you a bank account. But in this case, or even you go to a gold guy and you say, I force you to take this gold and move it to these other people. With the blockchain hype, there is plausible deniability. So Tether company can just tell the regulator, well, I cannot really move coins around because I'm issuing in the primary market and I'm redeeming in the primary market. I can do KYC AML in the primary market, but in the secondary market, everything is free. I cannot control it. Yeah, I can blacklist, so I can just make so that if you do something bad, I am forbidden from redeeming you this address. So that creates censorship, some degree of confiscation. Is not Bitcoin, but is Bitcoinish enough that many people now over the world are using USDT instead of sats. Why? Maybe they don't even know the difference. They will know the difference when either the dollar will hyperinflate or Tether will be forced to confiscate, because they still can, even if it's a little bit more ambiguous legally, or if Tether gets shut down, or if, but I think the most likely thing would be just the dollar becoming worthless, and so USDT becoming worthless. So now people can move to XAUT, gold. That's safer than the dollar from the inflation point of view, but that's hard from a business point of view, because with USDT, Tether can just use interest rates to make money. With gold, Tether has to pay a cost to store the gold. So Tether will have to reflect the cost on users as fees. And it's not clear this is a viable business model. The CFO of Bitfinex and Tether has some ideas, but it's challenging. And so my point is that BitTorrent is like Bitcoin. As long as it exists, it allows more centralized things to exist. And well, that's another funny story. USDT started on Bitcoin, but then they said, well, we are centralized anyway. Why do we really need decentralization? Decentralization is expensive. Let's just use Tron, which is literally a copy of Bitcoin with three guys with three computers, basically just this guy named Justin that will control the network. But he can just use the blockchain hype. So blockchain is a scam, mostly. But you can use it in two ways. To scam investors, like the ICO bubble, or to scam regulators. And that's basically stable coins. Now, I have to finish this in the next week. So I have just 3 slides. Let's maybe take one question and, well, 110. I don't even know if we can. One question here, and then we close it for the next.
No, I think that we are good.
Okay, sorry for not finishing. We finish this at the beginning of the lecture next week. Thank you.